This is sensitive. There's several of us here from Xarray and affiliated projects, so we'll just do a little round of introductions to begin with. So I'm Tom Nicholas. I'm one of the core maintainers of Xarray. I wrote the Xarray DataTree thing, which we'll talk about a fair amount in this tutorial, and I work on some of the other related projects as well. Yeah, I'm going to single people out so that they can introduce themselves as well. So we'll be taking turns presenting at the front, but any of these other people that I'm going to pick on now, you feel free to grab them at any point and pick on them and take them off for side chats, or put your hand up if you want to ask something, even if it's got nothing to do with the tutorial itself. That's part of the reason we're here, so that we can have these conversations in person. Yeah.
Hi, I'm Justus. I'm a oceanographer in Brest, France, and I'm also a Xarray core developer.
Hi, my name is Deepak Cherian. I work as a forward engineer at Earthmover, and I'm also an Xarray maintainer.
Hey, I'm Ian. I'm about to stand up and talk to you more. I also work at Earthmover. I'm the Xarray community developer, so I'm working on Xarray specifically for biology applications, but also in general. I'm going to talk to you about data structures in just a second.
I should have mentioned that I also work at Earthmover, who are one of the sponsors of this conference. Oh, hey.
Hey, folks. Oh, wow. Yeah. Hold it. If you end up with this microphone, keep it 3 feet from your mouth. So I'm Joe. I'm the CTO at Earthmover and an Xarray and Zarr developer. And that's it. Anybody else? Oh, yeah. Thank you.
Hello, everyone. My name is Negin Sobani. I work as computational scientist at NSF NCAR, and I work a lot with Xarray and the Pangeo ecosystem.
Cool, thanks. So we have 4 different sections. Our tutorial is split into 4 different sections today. The first one that we'll talk about, I'll just give you a quick overview. Is anyone not able to find the link to the home page that has the different sections? I'll take that as a sign of success. So the first section will be on a tour of Xarray's data structures, going from sort of the smallest data structures up to the biggest one, which will culminate with the DataTree data structure, which is this more complicated one that's been added to Xarray relatively recently compared to the other ones. And then after that, the second segment of the 4 segments of the tutorial will be about computations with Xarray, and we'll have a tour of basic computations you can do with Xarray, and then link that back to this sort of overarching theme of these hierarchical data structures with the data tree again. And then we'll pivot slightly and talk a little bit about Zarr. So really this tutorial is partly Xarray and partly Zarr. And there's never been a Zarr tutorial at SciPy, but you get sort of half a Zarr tutorial today. And this links to the theme in that Zarr has also a hierarchical structure and also is suitable for large data sets, and they play nicely together. So we'll have a section on Zarr and its use in the cloud, where it really shines in object storage. And then at the end, if we have time, we'll generalize that to some other storage formats, like scientific storage formats like HDF5, NetCDF, TIFF, and sort of compare and contrast. But yeah, that's the general outline. We have material to walk you through. We have some little exercises, but again, if you want to ask any questions or have a little chat about anything at any time, then please just put your hand up and someone will come and chat to you. We have a question. Okay.
Did you sign up on the tutorial website and get the login to the Nabari Jupyter Hub?
If you want to just view the content, you can also just go straight to the public Xarray tutorial website. If you just Google Xarray tutorial, you'll find the website. And then it's on the left-hand panel, there's there's workshops, and the workshops link to various notebooks, which are essentially just choice-picked content from within our wider. Our tutorial website has been built up over multiple years, and the workshop content that we go through today is essentially just picking out certain notebooks from that content.
Okay. Okay, so, yeah. So if you got this email from the conference organizers, SciPy 2025 tutorial instructions, hopefully you have gone to the user guide and made an account there, because then there's going to be a Jupyter Hub where it's all the environment is just going to work. Everything should run. So can you, if you do not have access to that, can you raise your hand real quick so someone can come and help you? One hand is what I saw, I think. If you do have access to this and are running into trouble accessing it, can you raise your hand? Awesome. Okay. So for those of you who do have access to this, you're going to go in here, go to Jupyter Lab, and then as she was saying, oh, mine already started, but the Mist-enabled one should work for every example we have, and then the Xarray tutorial is here, and you can click the download button, and then it will show up under Tutorials, Xarray tutorial, and then we're going to go, I can make this bigger. We're going to go to Workshops, SciPy 2025, and open up this index.ipy notebook file. And this will have links to all the notebooks that we're going to go to. Your laptop's here. Sorry, that's, yeah, I was trying to.
So if you all go to scipy.consite.dev first, and then there you have to register if you haven't already registered for other tutorials. You click on register with your personal email, and you have to update your password.
Yeah. I think whichever email you use to register for SciPy is the correct email to use. Yeah. Good. If anyone else is having a problem, can you let us know sooner rather than later? Like make a fuss. Can you raise your hand if you are in successfully to the Jupyter Hub? Okay. We'll wait another 2 minutes, check in again as the rest of you try to get in there. Let it finish building. Mm-hmm.
So anyone else have any problems getting on site, like the con site? So first let's do that, and then let them know about cloning. Okay, so the coupon code is SciPy 2025-desk.
It's right here on the screen too. Yeah, can someone? Probably not. There's instructions in the user guide if you are doing multiple tutorials. It has some section about what you're supposed to do. Okay. I think I'm gonna get started. I'm seeing a lot of people finishing. And if you don't have it running yet, that's okay, because the first bit is going to be some talking before we get to the first exercise, and then there'll be lots of opportunities to continue working and get it working. Yeah. I haven't. This screen is where I'm at. Like it's too small. Oh, sorry. So we're going to start by tutorials. After you've hit the download from this launcher, there's the Xarray tutorial. You can click the fetch, and that should populate tutorials, Xarray tutorial, workshops, SciPy 2025, and then index. And I'm okay. So as Tom was saying earlier, we're going to explore a couple different topics today. We're going to build up through the Xarray data structures that if you used it before, you might be familiar with, and if you haven't, we're going to explain what the core data structures that have existed up until recently are. And then we're going to get into the exciting new tools for hierarchical data tree, understand how some of the common storage formats you might have heard of, like HDF5, Zarr, how they conceptually map to the data tree model, and then have some cool examples actually using Zarr and Xarray and DataTree to do stuff. And there's going to be exercises and breaks interspersed throughout. So as you can see in our schedule here, so this introduction and setup, we're only slightly at double the time, which is, I think, reasonable given code setup. So I'm going to talk about the Xarray data model. Then we're going to take a break. Then Eustace is going to talk about computational patterns. Then we're going to take a break, and then we're going to talk about Zarr and the cloud, and then I/O basics, data models, custom backends. And so these are links. These are links that should hopefully take you to the correct notebook. And when you come here, you're going to see a lot of different Python kernels. And the one we want is you're going to have to scroll to the bottom, and the namespace is SciPy, and the environment is Xarray. And so you're going to click on that, and it will populate your notebook with a Python kernel that should run the code. So give you guys a second to do that. Okay, so the learning objectives for this section of the tutorial are that we're going to understand the basic structures that are available to us in Xarray. So we have data. We want to put it in Xarray to manipulate it and do stuff with it. What are the things, what do we put it into? How do we do it? So for this very first section, we're going to inspect the data array and data set objects. Then in the following section, we're going to work on data tree. We're going to learn how to do some super basic selecting of data that will set us up well for the computations. And then one other final point I want to make in this data structures is that just the examples, a lot of the examples that we're going to do are based out of earth sciences or geoscience, but these data structures generalize across fields. So we're going to have a really nice example from biology that shows how the data set can solve the same problems in biology that it solves in the earth sciences, and why that's so powerful. So we're going to start by understanding, we're going to build up an understanding of what this diagram means, because when I first saw, this diagram is incredibly informative if you know how to look at it, but when I first saw it, it was a lot to take in. So I'm going to build it up from first principles so we understand this. Then we're going to interact with these objects to actually understand how they work. And if you have a question and you're confused, please raise your hand, shout out, because you're not the only one confused. Someone else is also lost. So if you're lost, make it known, please. Happy to stop. So we're going to start with what's called an Xarray variable, which is important to understand, but is actually not something you're going to end up interacting with all that much. So the core, like the sort of lowest level of abstraction in Xarray is what's called a variable. And so this is what is in a variable. You have, yeah, is that a question? Okay, with environments. Let me keep going. So a variable has just a few things in it. It has, at its core, an array of data. So here it's an arbitrary dimension NumPy array, or a Dask array, or some other kind of array that has as many dimensions as it has dimensionality. And then you can have, it has names for those dimensions. So instead of dimension 1, this could be the time dimension. And it also has an attrs, which is an arbitrary dictionary of attributes that you want to add in. Metadata, this and that. So this is what a variable is, and everything else that we're going to work with is built out of, is effectively more and more complicated collections of variables arranged in helpful ways. So I said that the variable is the lowest level, but what you will actually interact with is the data array. It's sort of the lowest thing you'll interact with. And a data array is a collection of multiple, at least one, potentially more variables. So it's going to have one data variable that's, again, has dimensions, and it's sort of the data that you might consider working with. Then it also has the potential to have coordinate variables, which are sort of physical or meaningful coordinates that are associated with the dimension. So instead of a dimension being like index 1, index 2, index 3, this could be 1 minute, 2 minutes, 3 minutes, 10 months could be the coordinates that if you were to draw on a plot over time, like what would the x-axis be? So that's meaningful coordinates. So that's what these variables are. And this will make, we'll see this in a second. And then you also can have, there's attrs here. There's still dimension names because we build that up out of the component variables. And then the sort of formerly highest level of organization that Xarray provided was a data set, which you could kind of think of as a collection of data arrays, but it is in actuality is a collection of variables that have some shared dimensions, but not necessarily all shared dimensions. So all a data set is a collection of a bunch of variables, some of which could be data variables, and some of which we could treat as coordinate variables. And then again, there's attributes, and we compose we build the dimensions of the data set out of the dimensions that are available to us from the variables. And then when you grab one of these variables out, Xarray on the fly creates a data array for you to work with and have really handy computation. So that's a lot. I know it's a little abstract, and we're going to come back to this at the end after we've interacted with these. I think it's useful to show it at the start so we can have a mental image, interact with them, and then solidify our mental image. So we're going to start running code. So there's the best way to do this is with real-world data sets, and there's a Xarray tutorial data repository where you can automatically download a nice pre-made Xarray data set that we're going to work with today. So I'm going to download this, and we're going to start looking at this data set, and then I'm going to pause to let everyone catch up, and if you aren't able to get here, please let us know. So ideally, this second cell should have run for you. You might need to do a git pull in your thing depending on when you opened it, because there were some last minute changes to the index file. Alternatively, you can navigate to the intermediate and just click on the data structures intermediate. Okay, I'm going to continue and talk about looking at this data set. So when you have an X-ray data set, so this is air temperature data as over part of the world from the NCEP, I guess. And one of the really valuable things that X-ray provides you is in-notebook representation, HTML representation that lets you inspect the data and sort of see the shape of things. So you could imagine if I had a NumPy array of this, I would see shape 25, 29, 20, 53, and have to remember in my head what's latitude, what's longitude, which axis is time. And here, we can know that the shape of this array is 25 latitude by this time, by longitude. And what this is composed of, this data set, is there's these coordinate variables, what we were talking about earlier. And so these are each one-dimensional variables or arrays that have a dimension name associated with them, latitude, longitude, or time. And then we have our data variable that has the same dimension names as those coordinates. So it has time, latitude, and longitude associated with it. And then it has its own, so this is a three-dimensional data cube, and these are 1D. And then we also can have, again, arbitrary attributes in here. And we're going to be able to select stuff and use these to do really powerful computations. So just as a preview of why we're doing all this, why are we going to talk about what are the parts of this? One of the things that this data format, data structure enables us to do is to make semantically meaningful calls to code that create stuff. So instead of doing dim 0 time index 53, you can say dim equals time, plot the mean of the air variable, and you will just get out right away something where you can see the air temperature with a nice color map, and it's done the correct, put the axes labels in the correct place. So this is the advantage of having it all in one object that knows how things interact. This is sort of what we're building up to and why these data structures are so useful. So what is in a data set? Like I said earlier, it's a variable, or in practice, what you get out is a data array. Yeah?
Well, I was just wondering.
Oh, sorry.
When it gives us the summary that you saw above, that's information. One thing was kind of wondering if it was going to be there is units. Is that something that's intrinsic to a data set in this world, or is that something?
So
Little file. Yeah. You see there's a unit which
Xarray doesn't have direct support. Units are not a first-class citizen within the Xarray data model.
It'll at least tell you. You'll preserve that information.
So there are you can put arbitrary metadata onto the variable, data, etc. But it's just a completely arbitrary dict. And so here, it's just displaying a completely arbitrary dict that happens to have a key that says units, which is useful. It's informational. Xarray has support for units in a more integrated way, but only by wrapping objects from like the pint library, where the array type actually understands that it has units, but then it would appear in a different way to what you're seeing right now. But out of the box, Xarray doesn't have like a direct units hash.
That was a great question. Thank you. Does anyone have a question? No? All right. So now we're going to start interacting with the data set. And how do we interact? How do we actually get that error variable out? So the simplest way is this dictionary-like indexing. So you can do, no, thank you, Grammarly. You can do ds bracket and then the name of the variable that you want to extract. So in this case, we know there's a variable named air. And so we can just extract that by doing this. And this will give us what the representation of a data array instead of a data set. And so you'll see here that it shows the entire array because we know we only have one. In a data set, you can potentially have multiple of these data arrays, so you can't just display them all because it would stretch on forever. And so here again, it still has these coordinates. We've got the same indices, we've got the same attributes. We can know stuff about latitude and longitude here, or attributes. Similarly, you can just call dot the variable name, a little piece of magic for you. And you can access these things. And this is how you get access to the sort of underlying data to do your scientific computations with. Now, that leads to the next question, right? So what's in a data array? And hopefully we have some understanding of this from earlier, from when we looked at the sort of conceptual model. So it can have a name. In a data set, there has to be a name associated with it, but as a data array, it does not need to be. Dimensions. So here, in our data set, we have time, latitude, and longitude. You don't need to provide these. They will default to dim0, dim1, dim2, which is not super meaningful, but is useful because it is always there. And then like I talked about earlier, this data array is actually a collection of variables. And so there's these coordinate variables that Xarray keeps track of for us. And these we can also just extract and look at because they're ultimately just going to be given back to us as data arrays. So if you look at this, we extract the longitude, and it's just another data array that we can look at. And you can similarly get it through the coords like this. Like we were talking about earlier, adders is just an arbitrary dictionary that we can add stuff to. Here's what we added, who is awesome, Xarray, and all of you for being here, learning about Xarray. And then again, that all comes together as a nice data array. One other handy trick is that you can always access the underlying data of a data array. So in this tutorial, they're going to be NumPy arrays, but they can be Dask arrays, they can be QPy arrays, I think anything that supports the array API. You can access that directly via .data, so then you lose all your metadata stuff. And this is if you're passing it off to some function that expects a very specific type of array and doesn't know how to handle an Xarray. And you can always see this. Here it's a NumPy array. So two of the main data structures, reviewing, are data arrays and data sets that are effectively, they're sort of like dictionary-like collections of multiple arrays. And then again, looking at this, right? So we started, the core thing is a variable, which has data in it, and dimensions, and adders. Then out of those variables, we can build up a data array. Some of the variables are chords. One of them is the actual data. Or we can have a data set where we can have multiple data variables and a collection of coordinates. And one of the constraints of a data set is that you can't have two data variables that have a dimension where they have different. So if you have two things that are measuring something over time, but they measure different lengths of time, they can't live in the same data set because their time coordinates would conflict, which is what we'll get into with DataTree in a minute. So The other way to look at this, and the sort of classic way to look at this, is here's another view of what a data set is. So each one of these, this is not exactly the data set we have. You could imagine if we also have precipitation in this data set, then this would be an accurate representation. You can have latitude and longitude, which can be coordinates. They can be 1D or 2D, depending on your how you want to map them onto your data variables. There's dimension names. And so one set of just a set of coordinates that matches up with one data variable is a data array, and a data set is a collection of one or more data variables and associated coordinates and dimensions. So now we're going to go to our first exercise because there are these data sets. We can use them for things, but you have to be able to create your own instead of just receiving one from us. So in this first exercise, there's a function here that undoes all the good work that I'm going to have you do now, which is it destroys the data set and gives you just a bunch of NumPy arrays. And so the task that we'll spend a few minutes on is you're going to try to recreate a data set out of these parts. And so the hint that I would give you is that you can't just, I would make data arrays first and then go on to build data sets. And also to remember that Shift-Tab is going to be your friend here that tells you what the arguments to these functions is going to be. So we'll spend a few minutes on that. Move on? I don't know when it's time to move on. should I move on? I don't know when should I move on from exercise? So we do. Just a quick poll of the room. If you feel like you've achieved this or you feel like you're really stuck, can you, if you're sort of done with this exercise or feel like you're near done, could you raise your hand? Got one. All right. If you need some help, please let us know. Happy to walk around. I think we'll spend another 2 or 3 minutes on this, and then I'll show the solution, and then we'll keep on talking about data structures. All right. If you haven't finished it yet, no worries, because now I'm going to hopefully remember how to do it myself and show you how. So, like I said, the first step here is we're going to start making a data array, because we know data sets are composed out of data arrays. So, data array, and the data, we know that the data is this air temperature. So data air temp. If we run that, we would get this. We get these sort of confusing dimension names. And what you can do is you can say dims equals, and then the names of the dimensions. So in this case, that's time, and then latitude, maybe? Oh, geez. Latitude is the short one. Lat. Lon. And so then this would give us this nice labels, but we still don't know the actual sort of physical values for time. And so the way that you do that is, I told you earlier that they were the coordinate variables, and helpfully, they're also named coords in the argument to the function. So you can say coords, and then there's a couple different ways you can pass these in. The way I like to do it is as a dictionary, because that's the one I always remember. And so this would be data, time. And so now you can see time is bolded here, which is why you can tell that it's one of the coordinate ones that has a coordinate associated with it. And now we have these values in here. And we can similarly do the same with the other ones. Now, this may seem like a lot of typing, but the thing to remember is that you only have to do this with your data once from whatever form it comes from to get it into Xarray, if there's not already a pre-made to Xarray function, which there are for a lot of fields. And then once you have it in, you don't have to do this anymore, which is fantastic. And so you can put this here. You can do da.adders equals data adders. We can look at DA. And so this is a data array. We've reconstructed that. But if we had multiple of these data arrays that we wanted to combine into one thing, we would first make a data array out of the data, the individual pieces, and then we would make a data set. And remember I said a data set is kind of like a dictionary of data arrays? The way you create it is by passing a dictionary of data arrays into a data set. So data vars, And in this case, we only have one, so this is really simple. We say air, and we say this equals dA. And you can see that we've reconstituted our original thing, although I moved the adders lower than I meant to. What I really want to do and now we have the same data set that we started with. So it seems a little futile to destroy it and then rebuild it, but hopefully it demonstrates the idea that it may look like a big complicated object, but it's actually made up of a lot of simple parts that are easy enough to understand on their own. And all you need to do to make this, start at the smallest possible part, make that, and then just start combining them more and more and more. And then you can end up with this beautiful data set object that you can use for all sorts of things. One of the advantages of is that you can now save all of these things as one file rather than having to save the time array as one array and the error array as one array. They all can live in one single file. And Xarray manages that for you, which we're not going to talk about today, but it's in the documentation. Are there any questions, open questions about that?
Syntax so useful on the data array. So I need to specify the things, otherwise it doesn't work. Does it, like, isn't this a bit redundant? Is like with the chords and things, or probably
it is, I believe it is possible to, you can pass just the chords and not the dims. I think if you do it as, did you give it as a dictionary or as a?
As a dictionary and as a chords object, and both there's the same like.
So I think, oh, it's something like this. I always forget. I do it this way because I remember it this way every time, even though it's a little bit more verbose. But I believe, and someone can correct me if I'm wrong, that you can also give this sort of like collection of tuples, and it should work. Okay, so was it that's, I think what you're catching there is that Xarray is protecting you by saying if these dimensions, these numbers don't align, you can't assign them to the wrong thing. So that's a feature that it did not allow you to do that. Any other questions? Okay, great question, thank you. So just again to motivate, why are we doing this? If we went back to just our straight NumPy arrays and we wanted to make a plot of this, we could get our arrays like so, and then we could say, okay, lat, lon, and then we could do this NumPy style indexing that I think we're all familiar with, and we can take the mean of this over axis 1 if we wanted to. But, you know, what axis did I just take the mean over? Maybe you remember today because you've just looked at this, but if you come back in 2 days and you see temp mean axis equals 1, you have to there's this huge mental load that you have to go through of going and figuring out which axis is axis 1. Did I put a transpose in there ever? Is it still the same axis? There's all this stuff you have to keep track of. And so the advantage of Xarray is that instead of those things, like I was saying earlier, you can give time, select an actual time, like say time equals 0 instead of axis equals 1. You can say, I want the x-axis to be longitude. You can specify that instead of saying, I want the x-axis to be axis 0 or axis 2 or axis 1. And so you get to use these basically dimension names instead of just like numbers that are connected to dimension names, but Xarray does the keeping track of that for you. This extends, and we're going to not spend too much time on this, but this will sort of serve as a reference for the rest of the tutorial. But the same idea extends to selecting data. So you can select based on the values of the coordinates. So I can say, I want, I guess that's May 2013, and it will grab the air data for May 2013. Instead of me having to figure out which of those 2,900 time values corresponds to that date. Xarray handles that for us. You can also do slices, select multiple values, single values. You don't always need to remember the exact value, so sometimes you, for example, longitude values can have decimals. you remember pretty close. You can say, I want the nearest one, and it will do the math for you, figuring out what's the nearest as long as the data type is, allows this, it'll say, what's the nearest value to longitude, to this longitude? And you'll see you can get, it's 240 is the closest one. So we missed a little bit, but we can still find the right one. So these are some of the sort of quality of life improvements that Xarray gives you. And then we'll talk about this more in the next section, or I won't. Eustace will. There's a lot of really powerful computational expressiveness that comes out of this system. You can also, there's more indexing operations. Again, we don't need to get into all the depth of these right now, but they are all possible, and they're well documented on the Xarray documentation if you ever really want to get into them. Or we can talk about them during one of the breaks. And so this was a tour of what a data set and data array look like from geosciences. You have a question? No. But I want to make the point that we're not only constrained to geosciences here. These types of data structures where I have multiple arrays that have some overlapping dimensions but not all overlapping dimensions extends across a tremendous number of fields of science. It's a really common pattern. And Xarray does not only solve it for geosciences, even though that's what our example was. So hopefully this link works. Come on, click. Oh, I think the mist is not rendering properly. That link does work someday. But if you go back up and you go to intermediate and you click on the biology data set example, and again, select Xarray. So I'm a biologist. I did a PhD doing like microscope biology, taking pictures, looking at them, and I stored all of my data and worked with it in Xarray because it let me keep track of things like which fluorescent channel was which, and I have this mask and I want to save it with my actual images. And so this is an example. This data comes from the scikit image tutorial data sets, and what I did is I put it into an Xarray data set along with a segmentation mask, which is a pretty common task in biology. So, and again, we can just let this load. And just looking at this, we can if we came back to this data set weeks after we collected it, we could immediately have a good idea of what was going on. We could say, okay, it looks like we collected some images of cells, and we took some images that image the membrane, and some that image the nuclei of the cells, and it looks like we took a big Z stack of them. So this is just in microscopy where you take an image, and then you move up by like a micron, and then you take another image, and you go boop, 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 boop. And for each Z slice, you take two images, one of one fluorescent channel that might show membranes, one that might show nuclei. And then a really common post-processing task is to say, irrespective of channel, irrespective of Z slice, where is the cell? Where is each cell in the image? And so that's called segmentation. And if we look at one of these, you can see what I mean. You can see here, there's pretty clearly different cells. This is one guy, this is another one, this is another one, this is another one. And so a thing a lot of biologists do is they pre-compute a segmentation mask and then pass that along for all further computations. Now that mask often does not have Z dimensionality to it or channel dimensionality. It's just only in X and Y, maybe in time. Here's an outline of cell number 1, here's an outline of cell number 2. And so what I did here is I pre-computed it and saved it so we could all just load in and immediately have, without having to recompute, which is often pretty computationally intensive, you can see that I can take, again, these images. I can max project them to make it, which is a really good way in biology to make images look pretty. And you can see that I made a mask where there's individual cell IDs that are outlining the cells. And because we have these two things right close together and we never lose track of them, we can overlay an outline of individual cells on the actual image. And so there's nothing revolutionary here. It's just that we're keeping these pieces of data together in one nice data set, just like we were doing with the air data set. Yeah.
What's the squiggly one?
Oh, that is almost certainly junk. That is often dead stuff is highly autofluorescent. Is it? Wow, doesn't look like yeast at all. Thank you. Listen to her. I guess these are nuclei, so that would make sense. I work with yeast in a yeast image. If you saw that, 100% it would be dead. But so here, yeah, dividing cell. Because this is the nuclei, not the overall cell, like was pointed out there. And you can see, oh yeah, this guy would be in this big cell, which makes total sense. Thank you. So the point is not whether or not I know anything about human cells. The answer is apparently I don't. It's that this data structure works not only in air temperature data, but also in biological data. So the masks, the images that may or may not, they align on some of their coordinates, but not all of them, is the sort of fundamental connection here. So going back to our intermediate notebook, that leads us to the final exercise of this section, where we're going to motivate why the last data structure exists. So give just a few minutes to do this so we can catch up on our timing. This is another weather data set. And so now, unfortunately, I know even less about weather than I know about human cells, so I'm going to do my best. But there's two data sets that are in this data tree. And again, we're going to deconstruct it so we can understand why we want to have it in a data tree. They're looking at rainfall over a swath of land. So we can look at observed. We can see there's latitude and longitude values, and there's time, and then there's precipitation, how much water fell at any given time, any given place. That's an observed measurement. And we also have, it's called reanalysis, which is effectively, literally, modeling of how much precipitation should happen at any given place. This also has latitude, longitude, and time, so you might think, yes, we can combine these. But if you look carefully, the number of longitude and latitude values in reanalysis and in observed are different. And so if we try to combine these into one single data set, which is your task for the next 3 to 5 minutes, you will find out that there are problems that arise. There will be nans, there'll be errors. So remember that you can add to an existing data set by doing like some name, equals a data array. So take 5 minutes, try to combine these data sets, and then see what goes on. But first, what's your question?
Yeah, if you scroll for a second to the exercise instruction there,
Mm-hmm.
reanalysis and observed graphics, which
Oh, they sure did, yeah. I had a big headache this morning. That might be why, but I'll blame it on. So yeah, take a few minutes, potentially fix that, and then try to combine them and see what the data set of the combined data arrays gives you. And again, talk to your neighbor, be friendly, or raise a hand for help. Okay, let's not belabor that for too long, because I didn't really teach you guys how to combine things, but what I want to get to is that if we were to try to make a data set out of these two, with like XR data set, observed, this is again going to look pretty verbose because it's sort of a silly way to do things, but it's demonstrating a key point. Observed precipitation. This would work, but if we added on our reanalysis, you can see that when I just naively combine these two things, and I have my observed and reanalysis in one data set, because I want to be able to save these as one file, I want to be able to do whatever. Suddenly there's all these NANs that happen, and you could do resampling and reinterpolation, but maybe you don't want to do that. Maybe you want to keep them as they are. And that motivates, ultimately, what is our next and final section that I'm going to talk about, which is the data tree, which is the solution to this problem. So going back to the index, if we click on the data structures part 2, which does work, we'll talk about a data tree, which is how you have an Xarray object that has multiple different things that have potentially share some dimensions and potentially have incompatible dimensions, but live in the same object, which is really handy if you want to save your data, pass it to a function, make sure everything stays together nicely, refer to the shared components. So I'll give you guys all a second to get to this one. While you do that, talk about the learning goals, which is that we're going to understand what a data tree is, how to select some data on that, and what coordinate inheritance is, which will set us up well, hopefully, for computation. Yeah. Sorry. In the index file, data structures part 2. That's maybe there was a last-minute Git change. If you go to Xarray tutorial fundamentals, 01 data tree hierarchy is the place where this one is going to live. Okay, so I want to talk briefly about using the sort of same visualization that we were using earlier about what a data tree is. So a data tree is a collection of data set-like objects. They're not data sets. Like everything else in Xarray, they're composed out of collections of variables. So a data tree is like a tree. You can have child nodes, parent nodes, and any given group of a data tree or can have coordinate variables, it can have data variables, but then it can also have children. So in here we have a root group, which every data tree has a root group. And in our root group we have coordinate 1 and we have some data variables. These data variables only live in their node. They're not inherited. But some coordinate variables can be inherited. So in this case, each of the children share a coordinate variable that they inherited. So they both share a time coordinate variable. But they have their own latitude and longitude variables that are potentially different shapes than each other. So these data variables would be 3-dimensional. In this case, these data variables would only be dimensions in time. These would also be 3-dimensional, but they'd have different latitude and longitude, just like the reanalysis and observed example. Another example, which is the same thing, shows that the root group does not have to have any data in it. The root group could only have coordinates in it. It could have nothing in it. But a simple, useful example is something where the root group has the shared dimension that is inherited by all the children, and then the children have the same name of a dimension, but different coordinates on that dimension. So this will hopefully make more sense when we actually look at that data set we were just working on as a data tree. So we can look at this. And this, like everything else in Xarray, has a nice wrapper that lets you look at and inspect your data and understand what's going on. So here in this one, we have observed and reanalysis. And they have latitude and longitude, and then they have time. But you'll see also that there's time here, but there's not time in the observed coordinates. And that's because time is on the root level data tree coordinates, and that is inherited by all of its children, in this case observed. So just to look at that a little more specifically, we can have different groups. We have the root group, which is this slash, we have observed, and we have reanalysis. And you can access stuff just like we were doing before, and getting a node returns a new data tree object, which again looks pretty similar to a data set, but you can see there's a little different. Coordinates, inherited coordinates, data variables. And this syntax extends to selecting even further down, all the way down to the data array. And again, just like earlier, you can do this sort of string-based indexing, or you can do dot or method-based indexing. And then because this is a true tree structure, you can query parents and children of nodes. So you can look at the parent of reanalysis is the whole data tree. And the children of precipitation here is shown in this other way, confusingly. And then finally, this is sort of inheritance thing I was talking about. This is the time dimension that I was saying was inherited. So precipitation time. Find the root node, it's right up here. And that was inherited. And it's going to be, you can see here again, inherited time, the observed, and reanalysis also inherits time, but they have different latitude and longitude coordinates. And then this is the same images as above. Are there any burning questions about the start of a data tree? This is the super basic indexing. Yeah.
I apologize if you've already said this, but I guess when would you use a data tree versus a data set?
That's a great question. There's a couple different situations. I think this example here that we chose is one of the classic examples where you want to have things that live in the same object because you want to save them, you want to do stuff together with them, but you don't want, but they have different latitude, longitude, x, y coordinates. They have some incompatible dimensions, so they can't fit in a data set together, right? When we try to put these in a data set, it doesn't work properly. And so having them together is nice, but they're fundamentally incompatible. And so a data tree allows you to say they share some things, but not all the things. And that's really a really powerful abstraction. Another use case is if you have pyramidal image data. So like say you have multi-scale imaging either from microscopy or from a satellite, and it's expensive to compute coarsened versions of it. You might want to pre-compute them and save those. And a data tree is a really natural way to keep all of these different image scales into a same thing. Or if there's sort of intrinsic inheritance structure in your data, here's a data set that this data array has something that could truly be considered its child. And I want to keep track of that structure in the data, in my data frame. I want it to reflect the actual scientific structure of my data is when you might use, a couple of the examples when you might use this. So that leads us to the end of talking about data tree. And I think the exercise I'd be most interested in you thinking about is think through if there are any data sets from the field that you work in that might match up with those conditions where a data tree is helpful, where you think, oh, it would be great if I could have these in a data set, but I want these two things and they share an axis in an incompatible way. So for example, this precipitation with latitude, longitude, or in microscopy, if you have bright field imaging and then some laser scanning that has slightly different spacing than your camera pixels, they want to all go together. How do you put them together? Think of a data tree from that. And then I think we'll take if we combine that exercise, if you want to do it with the 10-minute break, we might even be back on schedule, maybe? So we'll say break/exercise if you want to do it. So we'll be back in 10 minutes? 10 minutes. expert arrays on disk, you can load them in such a way that they just end up being, like you're saying they're hierarchical but stored in some chaotic way. Yeah. So there are solutions to that. Has a starting from virtualized Zarr that actually does this really well and like assembles multiple things, never actually physically lines them on disk, but like treats them as if they were one thing. Like so for you, what is this thing, right? Behind the scenes, poses them correctly, and then you just load it as an X-ray, and you get all the benefits of working with X-ray. What kind of Zarr data do you have? Yeah, but what Zarr data? Oh, drones, like drones and yeah. So if you wanted to talk to me about like contact maps, like I'm your guy, but for geosciences, Joe is back. Ryan is far back. Was sitting here. There. Either of them. They will be much more careful than I am. So you're like, where's the state of like, how do I load this stuff into X-ray? Like that's what they do. What are you? So what are you? What is it? What? Who is your data coming from? Oh yeah. Yeah. So DataTree is probably there's like compatible dimensions. Some share some incompatible dimensions. You should. I could try it. Tom has had a lot of ideas about not even geosciences, like what is this? Tom and Ryan are both having a lot of thoughts about what is the future of how we combine different types of data into Zarr. Like, what is the best way to do this? What is your name? Shuma? What do you guys do now? Oh, like launch the satellite. And so it's gonna be in the internet, in the space, and then it's gonna come back down to you, and you're gonna store the data somewhere.
Just getting comfortable with this.
Oh wow! So you see the videos are cloud data, chunks. Okay. Which the many standards? Oh wow. Okay, yeah. images, right? So I remember resampling was not like a thing that I ever did, but there are all these really powerful group buys because basically every operating system is buy program stuff. But then there's a whole section of
This is a good
in
choice.
the user guide about resampling.
I think maybe you can do it.
So like resample, there's all these things, and because this is the sort of magic of the design of the data tree, is that like where they are all we're ever doing is we're composing the same elements on top of each other, and so data array, data tree is a container of the same things. Oh, resample, stack, remove. It knows
But this is
resample defines that sort of they're just like, and so not only is it central building, like that's enough. And then for me, the biggest thing is like, you tend to know it's not like, oh, you resample that. Sure, whatever.
Yeah, okay, yeah.
Yeah.
this basic.
I think so. Do any of these? Oh, that power. I'm going to steal that power cable as well. I think so.
Okay, great.
All right. Section 2. Hopefully everyone's back from their break with this very sensitive microphone. This little section will be about computations, and so we're going to go through some basic types of computations that you can do with X-ray objects in general, and then link it back to this overarching theme of hierarchical data with the data tree object and show what it looks like to apply some basic computations to that more complicated data structure. I actually just updated a link, so the notebook that I want you to open is not under intermediate, it's under fundamentals. I want this one, which is computation with Xarray, not 3.1 computation with Xarray. Should start with basic computation. Yeah, so the plan here is we're going to learn how to do Xarray supports basic arithmetic, supports basic NumPy functions on data arrays and data sets. We're going to see how that works. These kind of operations become really nice when they're dimension aware, and the particularly neat use case of this is reduction operations like means and sums. Those are all sort of like built-in methods to Xarray, but if you want to apply, you can apply arbitrary NumPy like ufunc operations to Xarray, which is an extremely powerful pattern, and we have an entire like hour's worth of content on that from a previous year if you want to go deeper there. But we're just going to like show you that that exists. And then the other nice thing that Xarray does is it does broadcasting for you based on named dimensions, which is great because it helps to liberate you from having to think about the difference between like axis 0 and axis 1 in NumPy world. Okay, so got the right kernel. Do our imports. All right, so this time we're going to use a different data set. Use this NOAA sea surface temperature product, so a geospatial data set. But it's basically gridded sea surface temperature over latitude, longitude, so space and time. And it's got a bunch of attributes again, showing that you can store like arbitrary extra information in here, as we saw before. And the dimensions are quite self-explanatory in this case. There's some extra little bits here which we don't really need to worry about for the purpose of this tutorial. So let's start off just by plotting what we've got. So we have our dataset object. The .sst is like syntactic sugar for just like get iteming the key for that particular variable, in which in this case it's called SST. So you can do .sst. And then icell is like select an index. We'll select along the time dimension, select the 0th value, so the first element along the time dimension. So this will return us a data array. This will return us a smaller data array. So we've got this like method chaining thing going on, which is taken from Pandas' API. And then finally, the data array object has this plot method, and these are just arguments to the plotting. So altogether, we end up with this matplotlib-powered plot, and you can see the vmin and vmax translated to the top and bottom of this color bar. You can see that Xarray has used all of the metadata that it has, such as the dimension names and so on, to intelligently label the coordinates, which is quite neat, so you don't have to do that yourself. And you can also see that because this is sea surface temperature, there's obviously no data over the land. These are just nans, but Xarray's handled this gracefully. So our data looks reasonable. Now, what kind of computations can we do with this? So let's first just talk about like scalar arithmetic. And so Xarray objects understand arithmetic operators. So for example, they understand the plus operator. And in this case, we can actually, if we want to convert the temperature units here, we could convert from temperature in Celsius to Kelvin simply by adding a single scalar to every element of the array. And what's nice about this is that Xarray's implementation of the add operator is clever enough to understand that when added to a scalar, it needs to like automatically broadcast that scalar across the entire contents of the variables, across the multiple variables in the data set, which means that we can get our result back with the altered values. You can see these are now have definitely had 273 added to them. And you can see that the nans are still nans, as they should be on the land. And Xarray's automatically handled the arithmetic there for you. And everything else was preserved. Like, we didn't lose any, we just applied the operation to every single element in the array, so we didn't lose any of the points. We still got the same time dimensions, we still got the same latitude, longitude, we still got the same coordinates, the same attributes, but we've got back a single data array with those coordinates on the side. Note that what we've done here is kind of like a very manual way of changing the units. As I mentioned when someone asked a question earlier, then Xarray does have an optional, like, deeper integration with units packages like Pint. We're not taking advantage of that here. We're just using this as an example of why you might want to add a scalar to every element of an array. And obviously, under the hood, what's actually happening is that NumPy is doing the adding of the scalar, because we are just wrapping NumPy. Xarray is doing the propagation of all the metadata around the outside. Yeah, Xarray is ultimately a pure Python wrapper of NumPy, basically. Question? That sounds suspicious. Can someone go and have a look, please? There are also some global flags that affect some of the attribute-related behavior. It could be something to do with that. But regardless of what happened to the attributes, you should see that the coordinates are preserved, right? Like the sort of auxiliary variables are still on the side. Interesting. Okay. Yeah. So whether or not you preserved, like, the arbitrary dictionary, this is a subtle but kind of interesting point, is that, like, the arbitrary dictionary of metadata that's attached to the Xarray object, there is no, like, correct way in general to propagate that through, like, an arithmetic function. Like, there's no correct rule for, like, adding to dictionaries in this sense. And so Xarray just, like, mostly by default just takes an approach of, like, you'd probably prefer to keep things than to lose things that you might have found useful later. The attributes are not really explicitly part of the data model in the sense that the main data model of, like, variables with name, dimensions, and coordinates actually has, like, well-defined rules for arithmetic that can be relied upon to propagate through. The attributes is this just, like, arbitrary dictionary that's stuck on the side that is sometimes useful, often very useful to serialize to an on-disk format. But because there's no, like, one true way to propagate those attributes, that kind of behavior is configurable. And it sounds like there's some kind of version mismatch or something, or like somehow my environment's got that flag set to the opposite value or something like that. But fundamentally, that's kind of like orthogonal to the main important, like, dimension-based broadcasting rules that Xarray has. Okay. We can, here we have another example of a scalar function. It's a nonlinear function now, and we are able, this is going to show off the fact that Xarray, like Xarray understands plus operator, it also understands the power operator. So we can call the power operator directly on the data array object here. It also understands what to do if you call a NumPy function on it. So Xarray defines like a special magic method that tells it what to do if you call certain NumPy functions on it. And so in this case, again, we're able to apply that sort of scalar formula, and Xarray basically sees that you're applying a NumPy ufunc to its object. It understands that that ufunc has no, doesn't do any reductions or anything like that. It understands that that ufunc is effectively like a scalar function, and so it applies it in exactly the same way that it did when you added a literal scalar, which is pretty neat. Like there's quite a lot of complexity there to make that work nicely. If you wanted to apply, it's pretty cool that we can do that, as I just said. Wow, I hadn't even read that before I went on that rant. But NumPy is obviously like a special library with special functions, and in general, you may want to apply any sort of arbitrary user-defined function. And sometimes even certain functions within NumPy don't obey NumPy's own rules if they're not technically ufuncs. And then you can get undesirable behavior, such as applying a NumPy function to an Xarray object, returning a NumPy array instead of a NumPy array wrapped by the Xarray. You've lost your metadata here. But if Xarray has this powerful top-level function which is intended for applying arbitrary user operations to Xarray objects, it's called apply ufunc, as in the NumPy applying the NumPy concept of a ufunc. So log is an example of a ufunc, but you can all sorts of things can be ufuncs. In this case, we can basically tell it how we want it to apply this NumPy nan to num function. And we basically say that we want to apply this function to this Xarray object, and our NumPy function also apparently needs some keyword arguments, and we can pass those through. And now we get the result we hoped we would get, which is it actually plugs through, pulls out the NumPy array, applies the user function to the NumPy array, and then rewraps everything back together. And this is a very simple example just to get around this like slightly unusual NumPy function, but this is actually an extremely powerful pattern, especially because you can start saying things like apply numpy.mean along the dimension time, and then it will understand that like it will do the rearranging of the NumPy array so that the last axis is the one that the mean will be applied along, and then you can basically start to like define your own statistical function and then apply it directly to the Xarray object. And this is a big rabbit hole, and if that sounds interesting to you, if you have your own like custom functions that you want to apply, then I encourage you to look up. There's on the tutorial site in the notebooks, there's a whole section on apply ufunc. It's very like internally, Xarray applies most of its functions using this apply ufunc thing. And I mentioned reductions. Reductions are generally very useful, very important functions. What they have in common is that they reduce the dimensionality, like there are fewer dimensions in the data in the result than there are in the input. And so a simple example would be if we have our data set is the sea surface temperature across basically all of the ocean's surface and over some time period apparently from 1970 to 2021, it would be reasonable to say, okay, what's the average ocean temperature over that time period? But you might want to say, okay, I want to know the average temperature over that period, but I still want to see how that average temperature varies over space. Like I still want to see if like the average temperature in the Arctic is colder than the average temperature in the tropics, for example, right? And so in that, what we would say that we're trying to do a reduction operation where we're trying to reduce the time dimension to be left with a two-dimensional array. In NumPy, you would be specifying axis equals 0. Xarray does actually allow you to do that for these reduction operations, but the encouraged syntax is to instead do it with the dimension names. And so in this case, we have our temperature, we take the mean over the dimension time, and you can see that the time dimension has disappeared, and what we've got back is a two-dimensional array, which still depends on latitude and longitude. And so if we plotted that, what would we get? Yeah, so we can see that the average ocean surface temperature is hotter in the tropics than it is in the Arctic, and that makes sense. Seems like a plausible outcome. And we still got the other metadata, and it's still all like lined up properly. Our array hasn't like flipped or shifted in any way. We haven't had to think about like whether or not the time dimension was actually axis 0, 1, or 2, which is a blessing because ultimately we don't really care as long as we took the mean along the correct dimension. We can also reduce over multiple dimensions. I mean, this is just shorthand for this. So in this case, we've taken the mean over time and also over latitude. So now we have something that varies only as a function of longitude, which is a slightly weird thing to do. If we do this, this is like a more useful thing that scientists actually do. Now, if we plot that, Xarray's plot method understands that this is now a one-dimensional object because we've reduced out two of the dimensions. And you can see that as a function of latitude, so imagine this graph like on its side, you can see that the highest average temperature in the world is around the equator, which again makes sense, right? But to get to this graph, we have taken a mean over longitude around east-west. And this kind of thing is like what I've originally found like super nice about working with Xarray, is that if you want to just like be like, oh no, actually I'd rather take a mean along this dimension, or I'd rather slice out over here or something, you can just do that super quickly and like interrogate your multi-dimensional object from different directions and different ways quite quickly. If you don't specify any dimension, then it assumes you meant all of them, which in this case gives you the average ocean surface temperature across that entire period, across the entire ocean surface, which apparently for this data set is 13 degrees. And we've used mean as an example of a reduction, but min, max, sum, standard deviation, they're all basically the same thing. They all take, they all reduce along at least one dimension. They can reduce along all of the dimensions. And they're all available as native methods on Xarray objects. And if you had some kind of reduction operation that wasn't available as a native method, then you would be looking back at that general apply ufunc pattern again. Yeah, so have a little exercise here. So if you want to try this, then the exercise is just to take the mean of sea surface temperature in both longitude and latitude, make a simple time series plot. I kind of already showed you how to do this. But yeah, have a go yourself just for a couple of minutes. Also just have a go with the other methods. Like Xarray has a large built-in API as well as extension points. So you could try like looking for standard deviation of things or finding the minimum temperature or whatever as well. And put your hand up if you have any questions or issues with that, and just give it a couple of minutes. All right, has anyone successfully completed the exercise? Has anyone tried it? Oh, I got one thumbs up, well done. All right, let's have a look at what the solution was. Taking the mean along both latitude and longitude and then plotting it. See, produces nice. Ooh, interesting. So what are we looking at there? So this is the average temperature of the entire ocean surface as a function of time. And so you can see some like presumably seasonal variations, like actual oceanographers nodding at me in the front here. Cool, okay. We're gonna move on to this hierarchical notebook now. So the idea of that notebook was basically to give you a little introduction to different typical like basic X-ray kind of computation operations. What I want to do now is instead go to this intermediate computation, this one hierarchical computation notebook. And here what we're going to do is take what we've just seen and apply it to this more complicated, newfangled Xarray DataTree data structure. So we want to be able to do basic arithmetic, and so these label aware, like the labels are the coordinate values basically. That's what we mean by like label aware. Or the names of the dimensions also are labels. So a reduction that says dim equals time, it's like you're using the fact that you've labeled one of the axes as the time axis, the time dimension, to do a label-aware reduction. We want to see that we can do similar things with Xarray DataTree objects. And then obviously the tree doesn't just have different variables in it, it has these different like nodes, these different groups. And we also have ways of applying functions across various nodes in the tree. So let's run this. All right, we're going to go back to this air temperature data set. We're going to open up the air. So what we're doing here is we're setting up our tree that we're going to use later. So we're opening up the original data set, and then we're going to do stuff to it that gives us a reason why we might want to put it in a tree. In this case, we're going to use this more complicated computational pattern that we didn't really talk about, but essentially we're going to change the resolution of the data. And we're going to do that. We're going to change the resolution along the time dimension. And so we're going to end up with the same data set, but kind of at different temporal frequencies, at different temporal resolutions. Do that 3 times, change the resolution to be daily, weekly, monthly, and then once we have all of those, we're going to stick them all together into one data tree object. So if we do that, it'll take a moment to run the computation. Now we have a data tree object that has 3 groups. The first group with the daily data, the second group with the weekly, and then the monthly. And you can see that the time dimension in each case is a different length. So the monthly data, 1 data point per month. So apparently we have 2 years of data here, which corresponds to 105 weeks, corresponds to 730 days. But otherwise, each of these is effectively like that single data set. They all have the same. We haven't done anything to the spatial resolution, to the latitude and longitude. And our data values are going to be fairly similar, but like in the real world, then taking these temporal averages along different sampling frequencies matters. So for example, in this monthly time series, in this monthly data, then you're not going to see like daily fluctuations because you've just averaged them out. And this represents like a vaguely real world use case where you have like different, maybe you ran some different like HPC simulations at different resolutions, or maybe you have like some observational versus like model data that comes out at different resolutions or something like that. But otherwise they're like very similar because you've deliberately put them on the same spatial grid, or they have the same types of like variables. So that's kind of how this is supposed to relate to a real world use case. So now we have this tree object. So you can think of it as like, in this case, you can think of it as like these 3 data sets, each of which is a different resolution, all together in one structure. We showed in our previous notebook that you can do arithmetic on that whole tree. So you can do arithmetic on the data set in one go, but we can also, like the data tree object also understands arithmetic. So if we do this scalar arithmetic, the data tree dot add magic method understands what to do with the scalar as well, and it basically will apply that arithmetic operation to every group in the tree, and then for each group it's dispatching the operation off to like the representation as a data set. So you could have a tree consisting of many simulations for different parameters or data across many different resolutions, and you want to just normalize them all in one go, you can just do that with like a single short call. And then similarly to how arithmetic is forwarded to the individual nodes, the individual like data set like representations at each node of the tree, we can do a similar thing with indexing. There's a subtlety here, which is that if I try to slice every node in the tree along time, and some of the nodes did not have a dependence on time, then normally Xarray would give me an error. But the implementation of datatree.isl is kind of worrying about that for you. So in this case, if we want to slice just a particular part of the like spatial domain, a particular section of latitudes, so I guess this is taking just like a little area of the Earth above the equator, then we can do that. And now if we look at the results, you can see that latitude has been selected down to only 10 points when it was previously 53 points. And these latitude values are should be consistent with that. Am I looking in the right place? I'm looking in the wrong place. That's why it looks weird. Yeah, you can see there's like only this smaller range of higher latitudes. But we're not selecting by the actual latitude values here. Because we use ICEL, so it's selecting by the indices. So actually this is not around the equator. This is at the near the Arctic, because the data is starting from top of the globe going down, apparently. If we wanted to select by actual latitude values, we would use the cell method instead, and then we could do things like select like all the data points that were at like 10 degrees latitude. But that's a fundamentally different operation than selecting the 10th latitude element in the array. Is different from selecting the latitude values equal to 10. And that's what the difference between the cell and iCell is. So you can see that it's just automatically propagated this onto all of the nodes. It's gracefully dealt with the fact that technically the root of the tree has no dependence on latitude because it has no variables. So it's slightly more complicated than simply doing a map over everything in the tree. Because it would have got to that particular node and said that dimension doesn't exist. Yes? I mean, this can be any valid slice. I think we just arbitrarily picked this example.
Say you have an open end, so we start with the beginning of the array and slice it.
Yeah. Yeah. But this is literally just a normal Python slice object, so it can be whatever you want it to be.
Is there a way to use like MI style slicing, like square brackets?
Sorry? There is for Xarray datasets, I can't remember if we got around to adding that particular method onto the DataTree class yet. But in general, there's a lot of different types of indexing that Xarray supports, and that's one of them. You got to search this like .loc, .location accessor thing in the documentation. So in that case, yeah, so that was an example of selecting for these particular indices of the array along latitude. But as I mentioned, you can also select for particular labels. So if instead we select the same time, now the time one is particularly clever. Xarray understands date times under the hood. So I think in this case it's actually basically selecting on the monthly data that time value corresponds to a single month, but on the weekly data that month corresponds to 4 different weeks, and on the daily data it corresponds to 30 different days, and that's all been handled gracefully, which is pretty neat. And this all works on dataset, right? The fact that it works on DataTree is just like a nice sort of confluence of separated concerns. And then we were just showing these indexing methods, but we can also do it with reduction methods. And so we've already seen how to do a reduction on a data set, but we could also do a reduction on a data tree. So in this case, we now have taken the spatial average, which means we've found the average temperature across the whole of our data set, which isn't actually the whole globe. It's like a section of a globe for this particular data set, but an average overall space. And as a result, that gives us, for this data set, that leaves us with a time series. And so now our data tree is containing 3 time series, but the time series have different resolutions, right? That was why we put them in different groups. So if we were to plot these individual time series, we would see that some of them have smaller scale fluctuations than the others because they've got higher resolution. So what if we wanted to apply a more unusual function? So let's say we want to apply an element-wise function. So for example, if we took NumPy log and applied it directly to the data tree, then this is currently not, so this probably could be supported in theory, but right now it's not. So we're just using it as an example of something where you're stepping outside of the beaten track of the API. And it gives you a relatively informative error, giving you suggestions of other things you could have done. But let's just imagine this was some complicated sort of scalar, or otherwise known as element-wise function that we wanted to apply to every single group in the tree. How might we apply that to all of the nodes in the tree, all of the groups in the tree? So we have this primitive called map over datasets, which maps over the datasets in the tree. And in this case, we have applied in this case, we've used an Xarray specific version of the log function, this ufunc of it, but I don't think you have to do that in general. You can define an arbitrary, this map thing basically just accepts any function that consumes and produces a data set. So a more general example, so as long as it follows pretty sure this is right. As long as it follows this kind of signature, then you can use it with the map over datasets function. So an example of a more complicated function that one could apply is, we haven't really talked about group by. That again is a whole other hour-long notebook within this tutorial repository. But in this case, we're basically subtracting a daily mean from the data is what this line would do. In this case, it would almost work, but not quite work, and that's because of the subtlety that I mentioned earlier, which is that if you try to map that over every single node of the tree, when it gets to the root node, in other words, the node with the empty path, it would say, well, there's no variables for me to apply this to. There's no data here. So what do you want me to do? And so one way to skip this for a custom function would be simply to deal with that if case within the function. And this is a kind of subtlety that for the built-in API, Xarray is like gracefully dealing with it for you. But if you're in general applying arbitrary custom computation, you need to handle it yourself because we can't know in advance what your intended behavior is. So in this case, this function now maps over all the groups and it successfully removes the daily averaged time from each of the groups. Okay, so this is one way you can apply custom computations over the tree. So one of the design principles behind the data tree thing was really like, as soon as it stops becoming useful to you, we want to make it easy for you to escape from the complexity of the tree and go back to the the relative safety of the data set, data array, or even if you need to, all the way down to the NumPy array. And so there are ways that you can just like get out of the data tree land, escape hatches, if you will. So for particularly complicated operations or while you're trying to sort of fumble around and work it out what you're trying to do, it might make sense to work on these simpler data structures as a collection of simpler data structures rather than like one big data tree in-memory object. And sometimes perhaps you want to break it up, apply functions to individual parts of it, and then reassemble it afterwards. So let's look at a different data set. We have this precipitation data. This one is kind of interesting, and there's a slight detour just to talk about why this is interesting. But in this case, we have a tree, and at the root of the tree, we do have some data. We have the time coordinate. Then, if we look at the groups, we have two groups, the observed group and the reanalysis group. So in sort of climate meteorology, then like observed is like measurements that were taken of the actual data. Reanalysis is almost like our sort of weather of best fit, given a range of observations and some model of how those observations are hopefully like physically connected. So in this case, you can think of the two groups in the tree as like experimental and model data. And so that's kind of a different conceptual use case of a tree in that we've kind of, it's like somewhat heterogeneous in the sense that we've put two different, like fundamentally different types of data in two nodes of the tree. We can also see something else interesting about this, which is that our time coordinate was defined on the root, but our child groups also have a function of time. And so this is actually an example of this coordinate inheritance thing that the tree can do that Ian mentioned briefly, where you can actually, on this subgroup, you can say, please give me the time coordinate, and it's also present on the children. And the idea here is that then the time is common to both the observed and the reanalysis data. So in this case, just so happens for this data set that the observed data was at a higher resolution than the sort of computed data. But in both cases, the time, for whatever reason, the time base is identical. And so we've taken advantage of that in this example by actually putting that common time coordinate into the root so that it's then just like shared between all of the child nodes downstream. That's not hugely relevant for what I'm about to show you, but it's kind of cool. And it's quite a powerful idea because it allows you to ensure that that time coordinate doesn't like become out of sync between the different groups. If it's shared in a common location in the root, then there's only one copy of it. But let's say we wanted to do some more complicated interpolation. We could probably do this with map over data sets, but let's pretend we couldn't for some reason, or we wanted to be fully sure of what we were doing, so we decided not to use that. Instead, we could pull out the individual data from the tree. So if precipitation is the whole tree, then this is a representation of just the root, just the data in the root node, or we could get a representation of just the data in one of these subnodes. And you can see if I do this, I still get this time coordinate. It's been like inherited onto the child node. And so we could, if we wanted to, pull the whole tree apart and just get all of its contents out by doing this. And if we pulled all the bits out and then we applied the computation we wanted to each result independently, each like node's data independently, then we could get something like we could interpolate just the observed data. And then once we had that result, so we could replace that with like interpolated. Then if we want to, we can reassemble a tree back together using this primitive, this from dict. So all of the trees can be thought of as like, the tree is meant to be partly motivated by a Unix-like file tree where you have these kind of paths going down and like subdirectories have only one parent, but a directory can have as many children as it wants. And any path within the file system can be represented as like /segment, /segment, /segment all the way down. The tree has the same structure, so the path to the root node is just like the slash or the empty path. And then the path to this node is like /observed. And it could go deeper, right? It could be like /observed /run1 or something like that. And this means that you can basically think of the tree as almost just like a key value mapping from these paths to the data that is contained at the location of that path. And so in this case, what we're doing is we're actually like first disassembling it into the data at each path. You can see this is the path to the root, this is the path to the observed data, this is the path. And we're doing that by pulling out with certain methods. And then what we're doing is we're reassembling it back again using this alternative constructor method, the from dict method. Probably it would have been clear if we'd split this out into two cells where we first rip it apart and in the second cell we put it back together. But the point is that you can create a tree from its sub-constituents in this like very manual way if you want to, which has a lot of uses, but one of them is to apply custom computations specifically to only certain parts of the tree. And it's like it's another nice form of escape hatch to know that like no matter how complicated your tree gets, ultimately you can kind of just think of it as like this dictionary mapping like string paths to the more familiar dataset objects. Yeah. So in this case, we split it up, apply these computations, reassembling it again, and we get back a tree which has the same structure because we told it to have the same structure. But we could have like renamed this or something, and then like this would come out different here because they're just string paths. So an exercise for you now to round off this section. Try and use this data set and see if you can compute the difference between the total observed and total like modeled precipitation, so modeled being the reanalysis one, and then plot the result and see how it goes. I'll give you a couple of minutes, and then this will be break time before we do another section. And just as a little teaser, after the break, we'll be switching gears to the Zarr related stuff. Yeah. All right, break time over, work time now. Just to finish up with this little exercise, we were asked to compute the difference between total observed and modeled precipitation. So one way to compute the total precipitation would be to take a sum. I feel like really technically this should be an integral, which is possible with Xarray, but let's just gloss over that. And then you could find the difference between the, so in this case what we've done is this sum operation, we've applied it to the entire tree. So we've used this reduction method on the entire tree. So this total thing is actually the total precipitation for all 3 resolutions. It's got 3 groups in it, which is going to be slightly different because integrating a fluctuating time signal that's like got different resolutions will give you different outputs. And then you could find the difference between the total precipitation in, oh sorry, I've just confused the 2 data sets we were working with. It's still true that we've computed the total over the entire tree, but in this case all that means is we've computed the total in the observed case and the total in the reanalysis case in one line, and then here we compare one to the other, so comparing across nodes in the tree, and then we can plot it like that. Yeah, so now we'll move on to some Zarr and IO related content. So this is like a little bit of a pivot. It has some stuff to do with the hierarchical content that we talked about with DataTree, and that Joe will talk about this, but like DataTree has groups, Zarr has groups, and they can play quite nicely together. Like they match each other's data models. But Joe is one of the main Zarr people, one of the Zarr core developers, so he'll be able to tell you and answer any questions about Zarr as a format, Zarr as everything you want it to be.
Is there a power plug here?
This one's a old style power
Oh,
plug.
nice. Yeah, perfect. I can do that. I think I can do that. Great. Let us. All right. Are we ready to do Zarr? Woo! All right. Zarr. Okay, so a couple disclosures. Was that a hand in the back, Ian? Can you sit closer up? You could zoom in. Let's try this. How's that? Better? Good enough? Okay, so there is one time in my part of the tutorial where you're going to get an import error, and I apologize for that. I have fixed it on my side, but it won't be fixable for you since you're all up and running. So we just caught that at the last minute. It has something to do with the Nibari environment you have. So that's disclaimer 1. If you're having trouble finding the notebook I'm going to walk through, it's called Intro to Zarr. It's in that intermediate folder in this tutorial. I'm going to make that go away now. But that's where the notebook is. And we're going to start now. Okay? Okay, so what are we going to do here? We're going to talk about the Zarr data format. We're going to learn how to use the Zarr Python library to read and write Zarr a bit. This is largely to get you familiar with what's happening a layer below Xarray. My favorite way to use Zarr is with Xarray. I work on the Zarr Python library, but I almost never use Zarr Python by itself. I almost always use it through Xarray. So if you're like looking for the fast and easy path, that'll come at the end of this tutorial, but we'll kind of build up towards that. and then you can put that in your back pocket for later. So, okay, so what is Zarr? Zarr is a data format. It's an open source, open specification, and community maintained data format for storing chunked, compressed, multi-dimensional arrays. What I mean by that is, so we've been working with arrays in the form of Xarray. Those are in memory typically. The way chunked compressed format works is you kind of break that array into pieces. Think like a Rubik's Cube, where each kind of corner of the Rubik's Cube is its own chunk. And then we run a compression algorithm on each of those chunks, and then we store them separately in either local storage on a file system or in cloud object storage, like we'll cover today. So that's what Zarr is meant to do. There's implementations in Python, in Rust, in R, in Julia, Java, C, et cetera, et cetera. So you can get Zarr in a bunch of places. You're at SciPy. We'll be using the Python implementation. So let's talk about the data organization aspects of Zarr. So it's a chunked compressed format, but it actually has a number of kind of primitive data structures that go beyond just the array. So first one is, the array. The arrays can be chunked and compressed. They don't have to be chunked. You can have a single chunk array. And you can also have uncompressed arrays, but these are both possible. Zarr datasets can have groups, so they can be hierarchical at any level, so you can have nested groups and arrays in them, so similar to the HDF hierarchical data format model. Zarr groups and arrays can have metadata. Okay, so we're going to look today at some JSON metadata from both Zarr arrays and groups. And inside this metadata, we're going to see stuff that describes the groups or arrays themselves, so things like the shape of the array or the data type. We'll also see user-defined metadata, so things like the units or the title or the description, et cetera. So we call that user-defined metadata. Basically, anything that's like a key value field can be stored as in Zarr metadata. Arrays have, in Zarr v3 at least, so just about a year ago or so, the latest version of the Zarr specification was released. So in that version of the specification, arrays grew the ability to have both a shape and named dimensions. Think like what we've been talking about with Xarray. In prior versions of Zarr, they just had a shape, and we used some other semantics for storing the dimension labels. And then we're going to use NumPy and Zarr together to do indexing today. And so we'll be able to kind of work out how to do various forms of indexing. Okay, so let's review using a, oops, come back. Let's review what I've just talked about now in a, I'm going to zoom out so that you can see this whole figure. Let's see. It just keeps getting bigger. Eventually, you'll get to see it. Okay, it's like too tall for my screen now, but you have it on your screen too. You can look at it. So just a bit of a schematic about kind of how the hierarchy works. So you have, group A here has two arrays in it, foo and baz, and then group B has an array called myArray in it. Each array, as I said, is broken up into chunks, okay? And so this is an array. You can see chunk 0, 0, chunk 0, 1, chunk 1, 0, and chunk 1, 1. And these chunks all have, some number of elements in them. In this case, they're all 3 by 4. To take a look at what this would look like at the store level, so maybe on disk or in S3, what we would see is the data format differs from, say, NetCDF or HDF because in typical applications, all the objects are stored separately in Zarr. And there's a bunch of benefits for, that we get from that, but just to look at what the layout looks like, we can see group A here, Zarr.json is the group metadata document. And then for array foo, we have Zarr.json, that's the array metadata document for array foo. Then we can see some chunks. So chunks have this C prefix. And then now we have BOZ, and you can see the metadata document, and then group B, my array, metadata document, and chunks. And inside of each of those metadata documents, you'll see something that looks kind of like this. So you'll have the Zarr format. This will be the node. You'll see the node type. So now it's an array. Now we can see that this was a 6x8 array, and that it is a data type of float 64. We can see that it's a regular chunk grid. That just means that all the chunks are the same size. It's the only option today, but it's still in the metadata. And then the chunk key encoding basically tells us how to connect the strings together for the chunk coordinates. So this just gives you an idea of like all the way down to the chunk level and all the metadata documents, how these all relate to each other. And hopefully you don't need to know much more about the format than this. If you want to know more, we can talk more about it. I'm happy to answer questions and all that. But the one thing I wanted to highlight is that, as I said, the Zarr datasets are broken into multiple objects in storage. And what that allows us to do is have concurrent readers and writers without any contention for the specific objects. And so, especially in object storage, that allows us to have many readers and writers operating on this data set at the same time. Cool. All right, questions on just the overview of the format before we get into the Python business? All right, great. Perfect. All right, so I'm going to go one wider. Is this an okay font size still, or a little small? Good. A little small. Okay. So here's what we're going to do now. We're going to use the Zarr Python library to create a bunch of arrays and groups, put those into different storage backends. We're going to set various attributes on these arrays and learn how to use the library. So first cell here is we're going to create an array, a 2D array, shape 40 by 50. The chunks are going to be 10 by 10. And we're going to write this to a local store, okay? And it'll be called test.zarr. All right, so we're going to run that. And by local store, I mean it's going to write to the file system on the computer where you're running your notebook. And so if you're on Nabari, that's going to be on the file system there. If you're on your laptop, it's writing somewhere on your laptop. That's what this test.zarr line is. So what we get back is this thing called Z, and we see that now we have an array of shape 40 by 50, and it tells us it's D-type. We can use the info property to get back a set of properties about this array, which tells us that we're using the Z standard compressor, and that we have, this isn't read-only. We can see how many bytes it is, et cetera, et cetera. You'll notice we haven't written any data there yet. We'll get to that in a second. We can take a look at the fill value. So there's various attributes on this array. In this case, the fill value is 0. And that allows, so we can actually go and then start reading data from this array, even though we haven't written any data yet, because we have a fill value. Zarr is automatically going to give us back a 0. So here we have the value 0 that came back. Now we can write data. So we're going to import NumPy here, and we're going to write ones to all elements in the array. And then we're going to, in the next line, we're going to set an A range from 0 to 50 for one row of this array. And then we'll take a look at that. So you can see now that all the values are 1. except for that top row, is now going from 0 to 49. Okay. You'll notice what we got back here is a NumPy array. So when you index into a Zarr array like this, what you're doing is you're fetching data from storage, and you're going to get that data back as a NumPy array. So Zarr works closely with, in this case, NumPy. It can also do CuPy arrays in some cases. Today we're only going to work on the CPU. Okay, so we can also set, like I said, arbitrary user attributes using the adders interface. So here we're going to just set the units and the standard name for this data set. We're going to print the adders. So we're going to write those two. Each time I run one of these calls here where I set adders, I am going to make a change on disk. So I'm going to update that Zarr.json behind the scenes. And then when I call z.adders, I'm going to go back and get that metadata. All right. So that's how to set both values in an array and metadata on the array. The next thing we're going to do is learn how to set or change the storage on the back end. And we're going to kind of learn, oh yeah, question first.
Yeah, this is, maybe it's about storage, but you mentioned before there are like Zarr libraries for several different languages.
Yeah.
Does that mean writing in one language and reading in another, it's independent?
Yes. Yeah, absolutely. Yeah, so you can write with, from C++ or something and then read it in Python. That's the job of the specification about standardizing how the data is laid out in storage. Yeah. Cool. Did I see another question? Yeah.
When does that file actually get opened? When you first made the data set, or every time you're writing to it?
There's some controls for that. So you can say say the shape of the array, that part of the metadata is opened once, and then it's immutable in that array object. The attributes are a different story. So in general, we kind of assume that if you're going to read the attributes, that you want to see what's actually on disk. And so it can happen multiple times. That's what I was trying to say here, is like when you call this line here, we're going to go get the attributes from disk. Yes. That's right, yeah. But there are controls for that. Like I believe there's something called cache adders somewhere in the API for where you can cache the adders. So. Okay, cool. So let's, you know what? It's really funny. I switched to this notebook. Maybe we're going to do both here. Give me just a sec. I think this is going to fail. Yeah, it is. All right. What I'm going to do is just grab a different notebook, and we're going to quickly. I fixed one thing, and I caused another problem. All is okay, though. All right. It's loading. Give me just a second here. Okay, I'm going to catch up. Okay, and then I'll zoom in. Okay. So I've just switched back over to the QuantSci hub, which I think should be fine. We're going to comment out one line together in a second. So what's going on here? So we have this store that we've been using. So if you remember, Z here is an array. And so z.store is a reference to the underlying storage. And this is pluggable, so we can swap this out. We could also have used S3 as a backend instead of a local store. But in this case, it's pointing to our file system. And we can actually look now at what's under the hood here. And so we can use the Unix tree command to do that. This is what was missing from my other notebook environment. And we can see that, so we have the since it's just an array, there's no groups here. We just have the chunk directory, and you can see the various chunks, and then of course you can see the Zarr.json as well. And we can open up that Zarr.json. We'll just call cat on that thing, and you can see that, again, it's a shape 40 by 50. It's all the things we input previously. So, one of the nice things about Zarr is you can, with the metadata is human readable. You can just open it up and look at it and see if it makes sense to you. It's not kind of hidden away in some, bespoke binary format or something like that. Okay, so yeah, here are those attributes we set as well. Okay, now we're going to do some work with hierarchies. We're going to start by creating a number of groups, and this is where you're going to hit a module not found error, and we're just going to comment it out. If you're running this on your laptop or something and you have Rich installed, then you'll be able to see the tree. But the Nambari hub didn't have that, so I'm just going to comment out this bottom line, and I think we hit this one or two other times. So apologies for that. In fact, this is where I can just switch back to here, and you'll get the full thing. So what we're going to do is create a new memory store. Sorry, I should stay with the microphone. Create a new memory store. We're going to create a root group. So the semantics here is the root group is at the root of the store. There's no parent above it. And then using that root group object, we're going to create some children. So we're going to create one called temperature, a group, and then another group called precip. So now root will have two children. And then in each of those groups, we're going to create a child array as well. And so that is what happens here. And you'll notice that instead of using the top level API in Zarr, say Zarr.createArray, we're using root.createGroup or temp.createArray. So that's creating children in each of those objects. And then, so you won't be able to see this tree line, but I'm showing it here on the screen. And so what we can see is just a visual representation of the hierarchical structure. Any questions on that? I know I've thrown a bit of a wrench by not giving you rich in your environment. Yeah.
Is there an option to store Zarr data in binary format for greater efficiency?
Yeah, so, well, for greater efficiency is an interesting point. There's definitely an option, greater efficiency on which dimension would be my question there. But you can put, if you want to just do a single object, you can put the entire Zarr store into, say, a zip file, for example. So there are anything with a key value kind of interface where you can do kind of random access to access individual chunks works. There's a draft specification for the zip file, but we could add others as well. But whether or not it will be more efficient is another question. So, okay, let's look at how we can access members of this hierarchy. So here is what it looks like to pull out just the temp group. And so up here, the first line that's printed here is just the group repr. And then underneath, we pull out some values from the T2M array in the temp group. And so we pulled out the first 3 rows and printed those. And they're all just zeros. We haven't written any data there. But this is, this returns an actual array, and then we did some indexing to get the data out. Take a look. We can see the group also has this info method, and then most of you won't be able to see this, but it obviously has the tree. Okay, at this point in the tutorial, we're going to shift to thinking a little bit more about the schema of the individual arrays and talk about the concept called chunking. So importantly, Zarr is a chunked format. It's a chunked compressed format for multidimensional arrays. But you have a lot of control as the writer of Zarr datasets over how those datasets are broken up. So you have an array, you're going to break it into pieces, and then you're going to compress those pieces. But how you break it up into those pieces is up to you. And this really matters because the chunks you write have to be able to be held in memory, then compressed, and then written. So you need them to be small enough. They need to probably align closely with your write pattern. But you also, the performance you get when you're reading data is also highly influenced by your chunk pattern. If you are writing, say, chunks that kind of are maps, so going back to the sea surface temperature data set we were working with before, that was a map. If that's the shape of your chunk, but you want to do time series analysis, you're going to have to read through a lot of different slices of the data set. And so there's trade-offs in how you do chunking. So in terms of the Zarr API, we can inspect the chunks themselves, the chunk schema, using the chunks property. And so here we just said z.chunks, we got 10 by 10 back. Okay, so I've already talked about a lot of this. So chunks are the kind of minimum unit of writing in Zarr. And so when you are, say, doing parallel ingest or parallel reads, we can distribute work at the chunk level, meaning one CPU can read from this chunk over here while another one works on the other chunk. They can decompress the data in parallel. And so this is one of the ways that Zarr scales very well, is by allowing you to completely separate workloads across chunk space. Okay. Let's now create a new data set here. So here we're going to create a data set that's much larger, 200 by 200 by 200. And we're going to create this first one, which is, has a chunk scheme of 1, 200, 200. So there's going to be 200 chunks along that first dimension. And then we'll create a second one. Oops, let's take a look here. Oh yeah, and then we're going to look at how long it takes to access just a slice along that, that first dimension. Now we're going to do the same thing, but we're going to transpose the chunks schema so that it's 200 by 200 by 1, and then we'll read that data back. See, that turned out to be much faster, right? Because that was just one chunk we had to read instead of 200. Cool. Does that make sense to folks? The difference in the patterns of like what we had to do to read. There were, 200 I/O calls that we made in that first example, and just one in the second. Cool. Okay. Now, try not to break our brains. We're going to talk about a concept called sharding, which extends chunking in some interesting ways. And so when you're working with large arrays and very small chunks, you can create a huge number of chunks. And so this is a good thing. Small chunks can be a good thing. They can allow you to read data more efficiently in certain ways, but they also have some drawbacks. One, they can be pretty hard on your file system. They can be hard to list or delete in an object store. And so there's reasons you might say, I want to have small chunks, but also, it might bring along some pain. And so sharding is supposed to fix some of those pain points. And the basic idea with sharding is that you still have chunks that are the minimum compressed unit, but we're going to write batches of those chunks together as a single object in storage. And so we can kind of think about it as a container that stores more than one chunk being a shard. The chunks themselves are still compressed individually, but we're just going to kind of stack them all together and put them in one object in storage. It allows us to have larger objects on disk, fewer objects on disk, but still small chunks. Question?
Within a shard, are chunks still able to be accessed
At random, yes, absolutely. So yeah, there's an index at the front of a shard, and you kind of have to go figure out where that is, but then, yeah, absolutely.
And I guess all of those are chunks assumed that you have to read the entire chunk every 10 minutes?
Yeah. Yes, but not shards.
But not shards.
Yes, yeah, absolutely. Yeah, because for almost all compressors, once you compress the data, you have to read the whole compressed block back to be able to read any of it. And I say almost all because there are a few partial read compressors, but for the most part, it's a true statement. So this is the idea of sharding, and Zarr just recently grew the ability to read and write sharded data. And so this is how you do that. So this example is going to walk us through how to create a new array. This is going to be 10,000 by 10,000 by 1,000. The chunks themselves are going to be smaller, 100 by 100 by 100. And, but the shards will be 1,000 by 1,000 by 1,000. So you can see now we have this nested data structure with many chunks in each shard, and then just a smaller number of shards in the array. So I'm going to run this here. And so now we can see what this looks like. We see the shard shape is now set on this array. And if we read and write data, we're going to be running through the sharding codec to write those. And one thing I really want to hammer home is that chunking and sharding are like highly use case dependent, and it's the sort of thing you have to tune for your application. There's not like a silver bullet, like this is the best chunking for all of us in our room, in the room. So typically you need to run some experiments to figure out what the right, if performance is something you're optimizing for, typically you need to run some experiments to figure out what the right set of trade-offs is for your application. Okay, now we'll look at compressors. And so here we're going to pull out just see which compressor we were using here. So we were using Z standard. Zarr works with a really quite a wide range of compressors, including BLOSC and Z standard and gzip. It also integrates with the num codecs package, which has like dozens more codec options. And so Zarr is highly flexible in terms of what it can, like what the codec pipeline or the compression pipeline, if you prefer, looks like, and that includes kind of array to array kind of pre-processing filters, as well as compression codecs. So if you don't specify anything in Zarr, you get the Z standard compressor, but you can override that. If you use the info complete function here, or method, I should say, you can get an estimate of what the compression ratio is. And so this actually went to storage, figured out what the size of all the different objects were, and then estimated what your compression ratio was. So in our case, we've written 20 chunks, and we see the compression ratio of 11. Cool. Okay. From here, I'm going to talk about a useful tool that we've developed for working with Zarr data in object store or over HTTP called consolidated metadata. And so if you remember the Zarr hierarchy that I talked about had a bunch of different metadata files kind of spread across the hierarchy. So you had a Zarr.json for each group and each array. And when you're discovering a hierarchy, you have to list the store to find, or the Zarr API has to go list the store and find out all the children. So it actually goes and looks at every key and says, are you Zarr.json? Are you an array? Are you a group? And that can be really expensive for very large stores, or very slow for very slow stores like object storage or HTTP. Actually, HTTP typically doesn't support listing at all, and so you can't do any hierarchy discovery. And so consolidated metadata is a tool that was developed specifically to solve this set of problems. And so what I'm going to show you here is we're going to create a new group and then 3 children, 3 new arrays. And then we're going to run a process called consolidate metadata. And what that does is it crawls through the store, finds all the metadata documents, and collects them into the root metadata document. In Zarr v2, it put it as a sidecar file called .z_metadata, and in Zarr v3, it puts it in the root group as a extension field. Now, if we go, I'm going to come back to this warning in a second, because this warning is actually important, so we'll unpack that in a minute. But now if we come back to Zarr, here we go, and we say open group, we can see that this group now has this consolidated metadata field. It's a bit of a mouthful, the way we wrote this, but consolidated .metadata, so that's the metadata for that, that group. And then it's the consolidated metadata field on the data class. But what you see is then we have this, this dictionary of metadata objects. And this is all the metadata that we had created in that store, kind of wrapped up into one JSON serializable object. And this is like a much faster entry point into a store if you have, many objects, many groups, many arrays, or if you just don't have the opportunity to list at all, like you would on HTTP. Okay, so this next section at the bottom here it says use caution when, and I'll just kind of talk through why you should use caution and why there's a warning when you use consolidated metadata in Zarr v3. So the first is, I think it's important that actually to say neither in the v2 spec or the v3 spec, neither of those specs have formalized consolidated metadata. So we're consolidated metadata today, though it's supported by most implementations of Zarr. It hasn't made it through the spec process, so it's a bit of like a living in the Wild West sort of idea. But there's other problems with consolidated metadata beyond formalized spec compliance or anything like that. The first is it's quite easy to end up with stale or incomplete consolidated metadata, meaning you can add an array after you've consolidated metadata and it not show up in the consolidated metadata part of the data structure. Or vice versa, you can delete data and have it not be deleted from the consolidated metadata key. This happens most when you're doing concurrent readers and writers. There's just like a lot of opportunities for race conditions. And then the last thing I'll say is that on local file systems, there's really just not that much to gain. It's quite cheap to list most file systems, and so you don't gain a whole lot. You just introduce some extra complexity and opportunity for errors. Okay, so that's consolidated metadata, and at this point we're almost done with this first part. And we see some Xarray code at the bottom, which is what we've been spending most of our day with, and so probably excited for that. So okay, so Zarr was designed from the beginning to work with object storage. It's one of its key differentiators relative to other scientific data formats. And there's a bunch of Zarr data on the cloud already today. So you can put Zarr in Google Cloud Storage, AWS S3, Azure Blob Storage, or basically any S3 compatible object storage, or over HTTP. All of these work, and it's a really powerful way to do parallel distributed computing and data sharing. And so here's a list of a number of places where you can find Zarr data that exist in the wild today. We have this tutorial has 2 different data sets we're going to touch. The first is some data from PangeoForge, the GPCP data set, and the second will be a climate data set, climate model data set. So now that I've been spending the last 30, 40 minutes talking to you about how to use the Zarr API, I'm going to basically convince you don't need to use that very often and instead just use Xarray. And so Xarray has the ability to read and write to Zarr directly. And what I'm going to show you here is how to do that over HTTPS. So we're going to point Xarray at this URL, and we are going to run it like this. Okay. And so what happened there is we went and read this data set from this exceed URL, and we got back a data set with a bunch of coordinates and one data variable, precip, with dimensions time, latitude, and longitude. And we can see that this is not a particularly small data set, has a fairly long time dimension. And so similarly with a data set, you can call toZarr, so ds.toZarr, and write directly to any Zarr store. So what we're going to do now is I'll stop talking for a second, and this is what the precip data set looks, or data array looks like. What we're going to do now is take this data set and do it's not showing up for me on the screen, but we have don't look at that, a bit of an exercise where we do a little bit of data analysis with this. And so you'll all be accessing this data set over the internet. It'll be going and talking to Exceed. And the task here is to calculate the mean precipitation for January 2020 in this data set. So you're going to need to open up the data set with Zarr, or with Xarray, slice it down to January 2020, and then calculate the mean. So we'll do that, and then we'll do a little bit more cloud Zarr in the final section here. Should I skip the cloud Zarr?
No, I was going to say, right.
Okay, great. No, it's fine. I could use more water, but yeah. No, we can wait till after the break. Should I tell everyone we'll take a 5-minute break now? Yeah, I mean, I'm at the end of this notebook, so.
Yeah, that makes sense.
Great. Okay, slight change of plans. We're going to take a 5-minute break now while you work on this exercise. So if you need to run to the restroom, go get a drink or whatever, we're taking a break. And then we just have one last section to run through. Any questions? Yeah.
This is a bit off topic, I'm not sure. But can Zarr be used as a means to understand patterns in the data?
I think Zarr can be used to store your data. This is how I'm going to answer your question.
So it's doing something, so
I see.
finding patterns.
Yeah.
Compress.
Yeah.
The question is how, by the way,
Mm.
these chunks and things like that.
Oh, that's interesting. Okay, fair. Now you got me thinking. Yeah, maybe. I mean, you'd have to kind of figure out how to interpret that information about, how much information content there is in each chunk, for example, and then relate that to, the spatial properties or what have you of your data set. But yeah, if information content is what you're after, breaking your data set into blocks is potentially interesting. Hey, up here we have a handful of Zarr stickers that in Eustace's hand. So if you're interested in a little Zarr sticker for your laptop, come find this guy. Yeah. But this actual, I want to say that this is a dask array right here. Yeah. Yeah, this is a dask array. Yeah, so Xarray supports, NumPy is the array backend, Dask is the array backend, or a handful of others. And so most of Xarray, like you can just use Xarray with Dask behind the scenes and not have to do a whole lot. Yeah, and it works great with Zarr as well because it kind of like spreads the workload out across the individual chunks. Yeah. Hey.
Is there a good heuristic for figuring out like chunk size?
We used to say 100 megabyte chunks is like a good target. Lately, we've been, especially with sharding, pushing that number way down. And so I still don't think that like kilobyte size chunks are a ton of value, but like megabyte size chunks or so, gigabyte size shards, you still have to write the whole shard at once, especially in the cloud you have to do that. So you have to assemble all the chunks inside that. And so sharding can be a total pain to write. It's like good for readers, bad for writers, sort of thing. So you just got to figure out your kind of read-write pattern. But yeah, with Zarr v3, Zarr Python 3, we used a lot more async IO throughout the library. It allows us to catch lots of small chunks more efficiently. So with that in mind, like smaller chunks kind of better pockets and spread the IO. So I don't know if that answers your question.
Yeah, no, it does. I mean, I'm using Zarr forever, but I've not used it in a way that there's a potential.
Yeah. Yeah. Cool. Yeah. Where do you, I need to get some. Yeah. You want to, I'd love to learn more about how you've been using Zarr for a long time. Yeah. What do you do?
Oh no.
All right, I've put my solution up on the screen if you're interested in seeing how I did the exercise. We'll take a couple more minutes on the break. All right, one more minute, and then we're going to get started again. Okay. We're going to wrap up the Zarr section with a kind of tour of CMIP 6 on the cloud and how to use Xarray and Zarr in Google Cloud Storage together to do some kind of basic data analysis access. So this notebook is called CMIP 6-Cloud. You can get to it through the link here. It's also in that intermediate folder under remote data. Okay, so this tutorial is going to cover three main things. I'll explain what CMIP 6 is before we get fully into it. But we're going to find this archive of CMIP 6 data in the cloud. We're going to access that data set remotely. We're going to pull out a single simulation and take a look at sea surface height. And then we will calculate some predicted sea level change in 2100 compared to 2015. So we're going to do that with Xarray and Zarr. And look, there's even some pandas in here. You'll see in a second. So before I get into it, let's talk about what CMIP 6 is. So CMIP 6 stands for the Coupled Model Intercomparison Project, Phase 6. It's a bit of a mouthful. What it is a kind of international collaborative effort to simulate climate change and the effects of greenhouse gases in the atmosphere, and then try to understand how different models predict the future climate. And so this has been going on for, 30 years or so, and there's been 5 phases of this. They skipped a number at some point. They went from CMIP 3 to CMIP 5. So there's been 5 of them. CMIP 6 has a big chunk of that data set. It's petabytes in size. The full archive is. About 2 petabytes of it has been moved to public cloud, and so that's what we're going to be using today. And so it's an open source data set. It's kind of, if you're a climate scientist, you definitely know what CMIP 6 is. It's the kind of hallmark future climate projections data set that exists for scientists today. Okay, so like I said in the last section, Zarr works with data in S3 with Google Cloud Storage and Azure Blob Storage, and there is a boatload of CMIP 6 on both Google and Amazon. The Pangeo project, which I've been a part of for a number of years, as have a number of us, kind of collaborated at one point on moving a big chunk of CMIP 6 into the cloud. And so part of that came with this catalog. And so that's what we're going to use pandas for. We just opened a CSV. And inside this CSV is just a listing of different activities and institutions and different metadata about all of these different data sets that exist in Google Cloud Storage. And so there's 514,000 different Zarr stores. And this catalog can be used to kind of figure out which ones are going to be useful for us. Someone said 5 million rows. I think that's 500,000 rows. But who's counting? Okay, so I'm not going to spend a ton of time unpacking this catalog. just to say that there's a field here called ZStore. That stands for Zarr store, and it's a pointer to the actual store for each of these data sets. Okay, so things like variable ID and experiment ID are kind of self-explanatory, but it's different ways of, it's how the data set's broken up into pieces. So we're gonna do a query that looks for the variable ID ZOS and experiment ID SSP 585. So SSP 585 is the like future climate emissions trajectory that we could be on, and then ZOS is the sea surface height above the geoid, and so we've just filtered that down. Now we have a smaller set of data sets, total of 272. We can grab just the first one, and we see here a path to a data set in Google Cloud Storage. And so we can see this is from NOAA GFDL, and we can take that data set and point Xarray at it. We're going to say consolidated equals true. We learned what that is, so we're going to open up this data set using consolidated metadata. And after a second or so, we have a data set up. So we have this large data set with its 500 by 700 in X and Y, and it has the sea surface height variable in it. So now what we can do is we're going to calculate, or we're going to extract the month of data closest to January 2015 and December 2100. So we're looking into the future on that one. And to do just a simple analysis, we're going to calculate the difference. All right, so that we're not fitting a regression or anything. We're just calculating the difference between these 2 months, and we're going to see what the model thinks has changed in these two. So we've extracted those two. We've now subtracted the difference. We're going to call that sea level change. I don't study sea level, so don't complain to me if you don't think this is a good analysis. Behind the scenes, this has been a lazy process up to now, meaning we haven't actually done that computation. The data hasn't been read. And something we haven't talked about today is how Xarray and Dask work together. But when we opened this data set using OpenZarr, we got back an array that was backed by a Dask array, meaning it's going to be kind of lazy and then in out-of-core processing and all of that. So that's not the point of this tutorial, but I just wanted to point out that's not a NumPy array. So this process of calculating the difference between these two was lazy. And then to materialize the result, we're going to call compute. So this takes a second. We're going to distribute that work over a number of threads, pull a bunch of chunks from Zarr. Okay, it's now done. And then we can make a plot. And here we see a difference in the sea surface height from 2100 to 2015. Cool. So some areas got higher, some areas got lower, different colors, red and blue. Okay. That was pretty cool. That was a couple petabytes of data. We didn't process the whole thing, obviously. We didn't have to download any of it. We streamed it directly into our Jupyter Notebook and did some analysis. And you could go change the fields, run this analysis for a different data set or for a different field, and still be able to access that data directly over the internet. So that's one of the really powerful parts of using Zarr in the cloud. Yeah?
Are there, can Zarr handle all types of data that Xarray handle, or is it limited to some subsets?
I think the answer is yes. There may be a few kind of, you probably could create some weird data types that we don't know how to handle yet in Zarr. But for the most part, I can't think of anything that I can't say yes to. Certainly in terms of dimensionality, shapes, chunks, that sort of thing, Xarray and Zarr are very compatible that way. Cool. Yeah. Yeah. Yeah, I'll skip this step here and we'll just do that. So now it did the compute on demand, basically. Yeah.
Does Zarr have its own diagnostics monitor for the
It does not. Dask does. So we could turn on Dask diagnostics and learn something about how Dask is doing the compute. There's some logging in Zarr, but this is something that we've been really interested in adding is more tools for understanding what's happening under the hood inside of Zarr when you make a request. Cool. Yeah.
I work with a lot of grip files.
Oh yeah.
I don't think that Zarr or have Zarr like how CSV file does.
Sure.
How would you go about, or is there a way that you can use Zarr?
Is Tom in the room? Yeah. Okay. Tom has a talk on Thursday. Search for virtualize Zarr and ice chunk, and I think you'll learn something there. Yeah, because the short answer is yes, there's ways to kind of connect the dots on these, but we don't have anything in the tutorial for it. All right. Other questions? All right. Cool. So we've got one section left in the tutorial. I'm not giving it, right? I'm not prepared to give it. So cool. I'm going to hand off to, I think, Tom. And then let's make sure to save a couple minutes for some announcements at the end. Sound good? Get this and this.
All right, so we got one more section. I think this will be a slightly shorter section and we'll end a little bit early. But the idea of this section is we've talked about hierarchical data structures in the context of DataTree, which is like an in-memory data structure. We have just had a bunch of stuff on Zarr, which is one very powerful storage format, which is hierarchical in the sense of it having groups. And so what I want to do here is kind of like connect the dots and bring it back to that overall theme of like hierarchical data and do a little bit of comparing and contrasting between what it means to have a hierarchy in Zarr versus what it means to have a hierarchy in DataTree versus what it means to have a hierarchy in a couple of other file formats. Just to kind of, so think of this as just kind of like a little advanced bit for anyone who's curious about like the difference between some of these formats and some of the design choices that were made within them. We're going to concentrate on some of the differences, but there's a preamble really, which is that, I mean, I think you probably all understand this by now, but it's worth repeating, which is that Xarray is not a file format. And sometimes you hear people who've sort of relatively new to using Xarray ecosystem to say something colloquially along the lines of like, let's save it as an Xarray or an Xarray thing. But that doesn't make sense. Like Xarray is an in-memory data structure. Like in order to save the contents of an Xarray dataset, a data array, a data tree, or whatever, you have to pick a file format that you're going to save it to, which canonically, historically, early on in Xarray's development was like netcdf. Now Zarr is like a pretty big deal as well. There are other formats that Xarray can read and write from as well. But and Xarray itself is not a persistent storage format. In theory, you could like pickle it, but that's ill-advised. You shouldn't really do that. It's like how a pandas data frame, that is not a storage format. Like CSV is a storage format, like Parquet is a storage format, and you can write pandas data frames to those formats, but the data frame itself is not a storage format. And so the Xarray was kind of inspired by pandas. You can kind of think of it as like an array version of pandas. You can also think of it as like an in-memory version of netcdf. So it's kind of taking the basic data model from netcdf and providing you with like an in-memory data structure that you can use for analysis, whereas netcdf is obviously for storage. But although it's inspired by netcdf, it's not totally identical to netcdf. And part of the reason for that is that netcdf ties itself, at least weakly, to these like domain-specific conventions, the climate forecast conventions. And one of the goals of the Xarray project was and continues to be actually like fully domain agnostic. Like it sees majority of use within, like the biggest communities that use it are like sort of geospatial and climate science meteorological communities, but there's no real design choice within Xarray that ties it to those communities. It's not tied to a particular metadata standard. It's not tied to a particular format. The data model of like multidimensional arrays and many multidimensional arrays is clearly not a concept that's specific to like meteorology. I personally got into using Xarray from plasma physics and nuclear fusion, and then like only transitioned towards like meteorology stuff later. And so, yeah, Xarray is not precisely the same as any one file format, and it's not precisely the same as netcdf, but for good reasons. One of those reasons being the desire to be completely domain agnostic. And because Xarray supports reading and writing to a range of file formats, but these file formats are slightly different, then Xarray is not quite the same as any of them. So when you read and write, there are like small choices or compromises that are made. And this is unavoidable because it cannot be consistent and also consistent with a bunch of things that are mutually inconsistent. That's not possible. The only alternative to that would be to have a huge number of like top-level global flags that changed key behavior that would just be even more confusing. And this makes sense in the sense that Xarray is not. It's slightly different to these storage formats because it's meant for a different purpose. It's meant for in-memory analysis. So the choices made are the things that facilitate it being useful for in-memory analysis while keeping it general to read and write from a range of formats, rather than making exactly the same choices as were made for some storage format and intended for a storage format. And this differentiates it from certain other projects. I'm kind of blanking on the name right now, but there are certain like data cube-like projects in some other fields, and it kind of feels like every time I come to SciPy, I find out about another one of these projects where like somebody in microscopy or neutron diffraction or something has like made a multi-dimensional array data structure, and I'm kind of like, you could have just used Xarray. But so anyway, one thing that you see over and over again between different file formats, scientific file formats, and one thing that Xarray also has is this notion of groups. And then if it has like nested groups, you have some like notion of a hierarchy. And this comes up, the exact meaning of what people mean by a group depends. Like a group in Zarr is technically different from like a group in HDF5. But they're all really like inspired by the fact that everyone seems to recognize that real scientific data sets often include like related but quite heterogeneous data. Like data that you want to store together or you want to analyze together, but it like violates some other kind of commonality, like it doesn't have the same resolution or something like that, or it doesn't quite align onto the same grid. So you want some way to put them like near each other, or some way to put them in the same file or the same Zarr store, but without them being like actually perfectly like able to line up against one another. And so let's just talk about a couple of different file formats and how this relates to the choices that were made in DataTree. So we'll start with Zarr because we just talked about Zarr for a bit, so this will be a little recap, but also Zarr has a particularly simple type of hierarchical structure. It has a tree of groups, but the groups are completely separate from one another. Like, if you put something in one Zarr group, that imposes no restrictions whatsoever on what you can put into another Zarr group. If you define something in the root of a Zarr group, you're free to like define something that's like almost the same but not in some awkward way in a child group further down if you want to. There's absolutely no restrictions made between the groups. Like, any Zarr group is basically ignorant of every other Zarr group. This is also true of arrays. Like, if you have two arrays in a Zarr group, there's absolutely no restriction on what you can put in each array. And the JSON metadata as well, like Zarr has certain sort of like required fields, like you have to tell Zarr what the shape is, you have to tell it what the D type is and so on. But then it has space for this like arbitrary JSON serialized dict, but it has no opinion as to like what fields are in that dict. So you could use it to store like units as one of the keys or something, or you could use it to put anything else. And this is because it's completely arbitrary, it's therefore completely domain agnostic. Other domains could come along and say, we're going to enforce some metadata standard upon the contents of this dictionary, and that is a sensible thing to do, but Zarr as a format doesn't make any requirements like that. If you're familiar with like TIFF and GeoTIFF, then like Zarr is analogous to TIFF here. It's not analogous to GeoTIFF. So we've seen this before, but yeah, the point is that these things are all independent from one another. Like, whatever I put in that JSON doesn't affect what I can put in this array. Like, they're free to vary. But so how does this relate to Xarray? Like, some of the statements I just made are not quite true of Xarray. So each Zarr array maps well and directly to a single Xarray variable at the lowest level, especially because one of the fields that Zarr does like natively understand is called dimension names. So the Zarr arrays are kind of like serialized NumPy arrays, but they also have this extra piece of metadata, dimension names. So when you write an Xarray variable to a Zarr array, you're actually writing in some values for those dimension names, so that when you use Xarray to read back from Zarr, that's how it learns that what you saved was like time, latitude, and longitude, rather than like axis 0, 1, and 2. Each Zarr group maps pretty well to an Xarray dataset object, because a group can hold like a set of an arrays, and an Xarray dataset holds like a set of Xarray variables. And you can use Xarray directly to open like an arbitrary group from a Zarr store by passing the group keyword argument. But Xarray is a bit pickier about what can go in a dataset than Zarr is about what can go in a group. So all of the variables, one of the reasons that Xarray datasets are useful is because they have these like shared dimensions across multiple variables. Like, if I have a time coordinate that has like length 50, and then I also have like my sea surface temperature that varies over latitude and longitude, but is also a function of time, it is a requirement that my time coordinate, if my time coordinate has 50 points, my sea surface temperatures must also have 50 points along time. It can't have like 30 points along time. We would say they have to be like aligned along the time dimension within a single data set. But that's not true for Zarr. Like, if you have two Zarr arrays in one group, one of the arrays can have like a time dimension of length 50, and the other one can have a time dimension of length 30, and Zarr is completely fine with that. And so in practice, this if you're reading and writing, if you're only interacting with Zarr via Xarray, this is never going to come up, because you're only ever writing things that you know how to read again. But it is technically a difference between these data models, and it's kind of like highlights one of the things that Xarray does this because it makes it easier to produce to have useful data structures for in-memory analysis, even though like we could have held we could have relaxed this restriction. It makes it less useful to do so. This means that, so it's technically possible to write Zarr data that cannot be opened with Xarray directly, although it can still be opened with any other library that understands the Zarr format. And this also links back to the motivation for DataTree. Like, this restriction is one of the motivations for DataTree, because the different groups in a DataTree don't have this restriction between groups. Like, that's why you're allowed to have like different resolutions in each group of the DataTree. Another subtle difference is that Xarray has like, an Xarray dataset has variables, and some of them are data variables, and some of them are coordinate variables. But Zarr doesn't have a concept of like data variables versus coordinate variables natively. It just has a bunch of arrays, all of which are like not different from one another. So in order for Xarray to preserve that information, it actually has to sneakily save an extra little metadata field into that arbitrary JSON dictionary, so that when reading it back, your Xarray client knows which ones are supposed, that time is supposed to be a coordinate. And then the tree of groups in Zarr maps to the data tree pretty well. I mean, deliberately. It's also quite interesting that these projects were like independently developed, right? Like, Xarray was independently developed from Zarr, but then the data models like happened to actually align super well. And then DataTree came later. And so you see that there's a lot of like convergent evolution within like the scientific data ecosystem in general, because even the choices that Zarr made are not the only libraries that have made similar. Like, the concept of groups has like come up in multiple places and multiple times. So yeah, the tree of Zarr groups maps to the data tree of groups pretty well. You can generally think of it as a set of independent Xarray datasets. It's like if each dataset is one Zarr group. Obviously, we saw that that's actually a slight simplification. Xarray has an API that just allows you to open all of them if you want. This returns like a dict of that function returns that, basically. So there's API just to get all of the groups independently together if you want them. Or there's API to open a single group as a data set, or there's API to open all of the groups as a tree. But Xarray DataTree, Zarr allows the groups to be totally independent from one another. DataTree, in order to implement those features like coordinate inheritance, where you define a coordinate at the root and it's available to you on a child, it has to make some alignment enforcing choices, which means that technically it's possible to write a Zarr store that has mutually unalignable data between a parent and child that can be opened as two Xarray data sets separately, but cannot be opened as a single data tree. And in practice, this like rarely comes up, but I just think it's kind of interesting advanced material for those of us who think about these formats and develop these formats, to think about like very subtle differences between these data models. Yeah, there's a similar subtlety with the coordinate inheritance. That's Zarr. So Zarr has this like very simple data model where Zarr basically enforces nothing between different groups. It enforces nothing between different arrays. Xarray and Zarr both kind of are have a lineage from the more venerable HDF group, HDF5. And HDF5 is this, like, most of you are probably familiar, but it's a general purpose container. It's a lot of its aims are very similar to Zarr, right? The main thing that separates Zarr is this like abstraction between the storage medium and the data model, and also the way that people use Zarr, and Zarr works very nicely for cloud object storage. whereas HDF5 is normally used as a monolithic file format. But HDF5 is a general purpose container for large heterogeneous hierarchical data. It has groups. The groups are very much like folders in a Unix file system, but interestingly, that includes the ability to have like symlinks. Like in a Unix file system, you can have symbolic links between groups. In HDF5, you can do something similar, even though it's not used super often. It massively complicates the the structure, because now your groups can have like cycles and they can have like self-referential links, which in Zarr is not possible. In Zarr, it just it doesn't support that, which means that like sometimes there are use cases where maybe you want that and it doesn't support it, but it also enormously simplifies what the tree means. HDF5 has this thing also called a dataset, but it's like an on-disk thing. And HDF also has this concept of a dimension scale, which is kind of like an Xarray coordinate. And then HDF5 has attributes, sort of arbitrary attributes in the same way that Zarr does, and it has some similar storage features with like chunking and compression. And then NetCDF4 built upon HDF5, but it's really technically an opinionated subset of HDF5. Like all NetCDF4 files are HDF5, but not all HDF5 files are NetCDF4. And NetCDF4 was an inspiration for Xarray, so now when you consider only this restricted subset, then it really becomes very similar to Xarray's data model. And so a NetCDF4 dataset corresponds to an Xarray dataset extremely well. But the way that it works on disk is like slightly different to the way that it's mapped to Zarr. Xarray maps to Zarr on disk. Yeah, actually, I should have put this in the other section because I think NetCDF4 does NetCDF4 forbid the loops within the groups? I think it does. And NetCDF, interesting, like NetCDF has an explicit concept of a dimension as a first-class object. Like there's actually like a dimension thing that you can like refer to within the structure of the file, whereas Xarray doesn't. There's no dimension object in Xarray. The dimensions of a data set are only like the set of the dimensions across all of the variables, and the variables have dimensions, but they're just names for the axes. There's no like capital D dimension object like anywhere in Xarray. And there are, I earlier talked about like Zarr, that you can't open. It's possible to create a Zarr dataset that you can't open with Xarray technically, although it rarely comes up. I think the same statement is true for NetCDF as well. And then just to like compare to a different file format, TIFF is another like widely used scientific file format, the tagged image file format, and it's a raster container. Widely used in like remote sensing and GIS and geospatial stuff, where they have these geotiffs, but it's also used in a bunch of other fields of science as well. And the TIFF format was originally developed for standardizing the output of like desktop scanners. So it's this like image format that's specifically only sets of 2D images, and sometimes called rasters. But so it's not actually intrinsically a multi-dimensional format. Like if you want to extrude those rasters a long time, you have to like, you can't really do that in a native way. You have to like abuse some of like the features of the TIFF format in order to do that. But nevertheless, lots of people are mostly only interested in 2D things, which is why it became one of the reasons why it became very widely used. And one of the communities that's like really very enthusiastically adopted TIFF is geospatial, where they've got the geotiff, and geotiff is basically a TIFF with metadata that conforms to a specific standard to encode things like exactly what projection on the Earth's surface you are using to create your map or whatever. Like. And TIFFs can do things like that are kind of analogous to holding multiple variables. They can hold like multiple spectral bands. For example, for like an RGB image, you'd need like an array of the R values, an array of the G values, an array of the blue values. And you can put sort of extra arbitrary metadata in as alongside any. Like GeoTIFF is essentially a metadata standard that requires certain tags, but you can put arbitrary extra ones as well. Supports some compression, a bit less flexible than Zarr's compression framework, but it does support a few different compression options. And then people took, when the cloud was a thing, people took TIFFs and reorganized them internally to put all the metadata up front to make them cloud optimized. And people have also done the same thing for HDF5. But if you take that logic to its extreme conclusion, instead of moving all the metadata to the front of one file, what you really want to do is move all the metadata for like 1,000 files outside of that file to one place where you can go and get it. And once you start doing that, you've basically just reinvented Zarr. I actually have a whole blog post about this that I might shamelessly link to right now. Because if that's interesting to you, then this one. Yeah, if anything I just said is interesting, you'll probably enjoy this post. Okay, nearing the end now. So how does TIFF relate to Xarray? So the TIFF is fundamentally like two-dimensional. It's inherently 2D per band. And so if you need some data that's more than 2D, then one of these other formats that's truly multidimensional is a better fit. But each 2D band does map well to a single Xarray variable. It's just that variable is going to be 2D. But TIFFs don't have named dimensions for the two axes. GeoTIFFs might have a convention for it, or other formats might have a convention for it, but like raw TIFFs don't have that. And then the IF, I forget what the acronym IFD stands for, but it's like a subdivision within the TIFF file that's analogous to groups. They can be mapped to groups in Xarray, which can be useful for multiple, like you can store multiple resolution data in a single TIFF. And some people think, and that in geospatial land that's called overviews. Some people think that that's like special to TIFFs, but it's not. It's just a thing you can do with groups. You could do the same thing with Zarr. You could do the same thing with NetCDF4. And you could open them up in the same way to a data tree that has multiple groups of multiple resolutions, because it's all like fundamentally kind of the same idea. Yeah, there is some TIFF support with Xarray. You can use this library called RioXarray, Rasterio, to open GeoTIFFs into Xarray and write them back out. I'm not totally sure if someone's actually written a general TIFF opening function for Xarray. I think you could. There might exist one in the wild, but I kind of just put this in as like completing this trifecta of well-known science formats. And at this point, you might be saying, well, like, these formats are all really similar to each other. They all have groups, they all have like multi-dimensional arrays, they all have arbitrary metadata, they all have compression. Like, people want to cloud optimize all of them. A lot of them, they often have dimension names. So like, if we can map them all to Xarray, can we map them to each other? And the answer is yes. You should come to my talk on Thursday where I explain how you can do that. And I basically talk about how you can use the Zarr API to open data from NetCDF4 or TIFF directly in like a cloud optimized way where you're like pulling out these chunks in parallel. So you can basically get the speed advantages of Zarr whilst opening data that's still in the old formats, which I think is cool. But yeah, that completes the overall arc of the talk, joining up the different formats with the hierarchical ideas, both in memory and on disk. And so I don't really have an exercise for you, but Joe has some announcements.
All right, we've reached the end. About to send you on your way with some new Xarray and Zarr skills. But before we do, let's see if this just, yeah, look, tutorial announcements. Okay, 2 quick announcements, 2 quick slides with multiple announcements on each slide. It's a hierarchical announcement. Okay, is this the first SciPy for anyone in here? All right, there's a lot. Oh, wow. Oh, my goodness. Okay, this conference is kind of famous for puns. What I just did, there's many more, much better puns coming up. Okay, so I just have a couple announcements that kind of span both the Earthmover team, but also the full set of folks that helped put this, tutorial together. So a couple things. First, tonight, informal, most of us are going to head down to the Seven Seas tap room. There's also a message in the SciPy Slack about this, so just want to say we're going to be there if you want to come down and get a drink or some falafel or smash burger, whatever you have. We'll be hanging out there. 6:30 is the time. There's an address there. You're going to probably want to write that down or something. Thursday night, Earthmover and Development Seed. Where is Development Seed in here? There you are. Chuck's here. So we are co-hosting a Open Science Happy Hour. There is a link there to sign up and figure out where it is. I'd love to have you come if you want to. So do that. And then right outside the door, for the rest of the conference, the Earthmover team is going to have a booth. You'll see us. But just come say hi. We'd love to talk to you about Xarray, Zarr. We didn't get to tell you anything about Ice Chunk today, but I'm sure you'll hear more about it as the conference goes on. But come by the booth and see a demo of it, and we'll use Xarray and DataTree and that sort of stuff along with it. So those are the announcements about events and or places you might want to take yourself. Oh, there's more. This slide is about talks and posters that the tutorial team has at this conference. And so I thought I'd just shout them out. Tom has a talk with another guy named Tom called Cubed Scalable Array Processing with Bounded Memory in Python. So if you're into like Zarr and Xarray stuff and also want to do it at scale, go see Tom's talk on Cubed. Yes, if you've heard of Dask, I've had at least one person come up and ask me about Dask, so that would be good. Ian, who gave the opening part of the tutorial, is giving a talk on Xarray across biology. Where are we and where are we going? So go see that. Tom also has a talk on virtualized Zarr and Ice Chunk, which he just pitched to you, and so you should go see that. Deepak has a talk called The Brave New World of Slicing and Dicing Xarray Objects, so go see that. 3 posters, one on group by stuff in Xarray by Deepak, one by me on Ice Chunk, this open source cloud native transactional storage engine for Zarr. And I think you'll be very interested in that. And then finally, by Eustace, fast and scalable general geospatial regridding. So, no.
Yeah, there's,
did I miss one?
tomorrow, yeah, on CGS.
By you? Yeah. I'm sorry, it didn't copy and paste effectively. And did I miss one from you too?
Yeah.
I thought I had it in my list.
Well, Zarr, it covers Zarr.
Zarr and GPU, that's right.
Yeah, it covers optimizing geospatial.
Okay. I had these on my list just a little bit ago. I'm very sorry to both of you, but I wanted to include them. Okay, so yes, there's a whole nother talk on Zarr and GPU. There's also, I believe, a poster on a similar topic. And then, yeah, on what is XDG? Yeah. Discrete global grid systems with Xarray. So, cool. Any comments, questions? Thoughts from the tutorial organizers? Ian. Yeah. Cool. Yeah. Okay, very good. Yeah, sprints Saturday and Sunday. So if you're sticking around for those, knock some X-ray stuff out. It'd be awesome. Yeah, thank you for coming. This was fun. And